Russell's paradox arises when we ask a simple but deep question. Does the set of all sets that do not contain themselves include itself? If it does, then by definition it should not. If it does not, then it should. This creates a contradiction. To understand why this is a problem, consider how sets work. A set is just a collection of objects. Some sets contain ordinary things, like numbers, letters, or shapes. Others contain more abstract things, including other sets. Some sets even contain themselves. I'd love to invite you to share in the comments where you're listening from and what time it is. It's incredible to think about how we're all connected through these stories and ideas. If you enjoy these thought-provoking explorations, consider subscribing to Tired Thinker so we can keep bringing you reflective narratives. Now, settle in, get comfortable, and let your imagination drift as we delve into the mind-boggling paradoxes and mysteries. For example, the set of all things that are not cats does not contain itself because it is not a cat, but the set of all abstract ideas might contain itself because it is an abstract idea. Now, imagine a set that includes every set that does not include itself. Call this the special set. If this special set includes itself, then it should not, because it is only supposed to include sets that do not include themselves. But if it does not include itself, then it should, because it is exactly the kind of set it is supposed to contain. This contradiction makes it impossible to decide if the special set should or should not be in itself. This paradox challenges how we think about sets. In everyday life, it is rare to think about collections of things in such an abstract way. But in mathematics, being able to define sets clearly and consistently is important. The contradiction in Russell's paradox means that there is a flaw in how we define sets. To see why this matters, imagine a library catalog. Some catalogs list every book in the library. Others list only books about specific topics, like history or science. Now imagine a catalog that lists all catalogs that do not list themselves. Should this catalog include itself? If it does, then it should not. If it does not, then it should. The contradiction is the same as in Russell's paradox. Before this paradox was discovered, mathematicians believed they could define sets in any way that made sense. They assumed that if you could describe a group of things, you could call that group a set. But Russell's paradox showed that this assumption leads to contradictions. If sets are allowed to be defined this freely, then some definitions, like the set of all sets that do not contain themselves, create logical problems. This discovery shook the foundations of mathematics. At the time, mathematicians were trying to build all of mathematics on a firm logical foundation using set theory. If set theory contained contradictions, then the entire structure of mathematics was at risk. If basic logic could lead to contradictions, then mathematical proofs could no longer be trusted. Russell's paradox showed that not every collection of objects can be called a set. This forced mathematicians to rethink the rules of set theory. To fix the problem, they created new rules that prevent paradoxes like this from happening. One solution was to change how sets are allowed to be defined. Instead of allowing any description to define a set, mathematicians created stricter rules. These new rules make sure that sets cannot contain themselves in ways that lead to contradictions. This change made set theory consistent and avoided the problems caused by Russell's paradox. Another approach, called type theory, avoids the problem by organizing objects into levels. In this system, sets can only contain things from lower levels, not things from the same level. This prevents a set from containing itself, removing the possibility of paradox. This paradox also has practical implications beyond mathematics. Logical contradictions can appear in computer science, philosophy, and even everyday decision-making. Any system that defines things in terms of themselves can run into problems similar to Russell's paradox. For example, consider a set of rules for a game. If one rule says that players must follow all rules except this one, then it is unclear whether the rule applies. If it does, then it should not. If it does not, then it should. The same problem appears in legal systems when laws contradict themselves. Russell's paradox shows why careful definitions are important in any logical system. Even in language, similar contradictions arise. The statement, "this sentence is false," creates a paradox because if it is true, then it must be false. But if it is false, then it must be true. Russell's paradox is a mathematical version of this problem. This paradox also influenced the development of formal logic. It led to more careful thinking about what can and cannot be defined. The search for a solution to Russell's paradox led to deeper discoveries about the limits of logic and mathematics. One major result was Gödel's incompleteness theorems. These theorems showed that in any system of mathematics, there will always be true statements that cannot be proven. This means that no set of rules can capture all of mathematics without running into problems like Russell's paradox. Russell's paradox is a reminder that logic is not always as simple as it seems. Even ideas that appear clear can lead to contradictions if they are not carefully defined. It shows that mathematics, like any logical system, needs solid foundations. The impact of this paradox extends beyond pure mathematics. It shaped the way mathematicians and logicians think about definitions, rules, and consistency. It led to new branches of mathematics that focus on making sure logical systems do not contradict themselves. Even though most people do not encounter Russell's paradox in daily life, the ideas behind it influence many areas of modern thought. It helps ensure that computer programs work correctly, that legal systems remain consistent, and that logical arguments make sense. It is a fundamental problem that helped shape the way we understand logic and mathematics today. By exposing a flaw in how sets were originally defined, Russell's paradox forced mathematicians to refine their ideas. It showed that not everything that seems logical is actually possible. It proved that even basic ideas, like the concept of a set, need careful examination to avoid contradictions. The paradox may seem abstract, but its consequences are real. Without solving it, modern mathematics would not have a firm foundation. It is an example of how questioning simple ideas can lead to deep insights. It reminds us that even the most basic concepts can hide unexpected surprises. Russell's paradox is not just a mathematical puzzle. It is a lesson in the power of careful thinking. It shows the importance of precise definitions. It demonstrates how even small logical issues can lead to major problems if left unchecked. By understanding this paradox, we gain insight into the nature of logic itself. We see how rules and definitions shape the way we think. We recognize the need for clarity in any logical system. Russell's paradox is a reminder that even in the world of mathematics, not everything is as simple as it seems. The Barber's paradox is a simple yet puzzling idea. It asks us to think about a barber in a village. The rule in this village is that the barber shaves all those who do not shave themselves. He does not shave anyone who chooses to shave on their own. At first, this rule seems clear, but then a question arises. Does the barber shave himself? If the barber shaves himself, then according to the rule, he should not. He only shaves those who do not shave themselves. But if he does not shave himself, then he must, because the rule says he shaves everyone who does not shave themselves. No matter which way you look at it, there is a contradiction. This is the heart of the paradox. It creates a situation that cannot logically exist. To understand why this paradox matters, we need to think about why rules like this lead to contradictions. The problem arises because the rule is too rigid. It tries to classify everyone into two groups. One group shaves themselves, the other does not and gets shaved by the barber. But what happens when the barber himself is part of the system? He does not fit into either group. This is where the contradiction appears. One way to approach the problem is to ask if the barber even exists under these conditions. If such a barber were real, he would have to follow the rule exactly, but the rule creates a logical loop that cannot be resolved. So, the only way out is to conclude that such a barber cannot exist in the first place. The paradox shows that sometimes defining things too strictly leads to impossible situations. This type of reasoning is not just a curiosity. It has deep implications in logic and mathematics. The Barber's paradox is a simplified version of a more complex problem called Russell's paradox. British philosopher and mathematician Bertrand Russell discovered it while working on set theory. He noticed that some sets, or groups of objects, could be defined in ways that led to contradictions. To see how this works, think of a library that keeps a catalog of all books that do not list themselves. Most books do not mention themselves, so they go in the catalog. But now ask, should the catalog itself be in the catalog? If it includes itself, then it should not be listed, because it only includes books that do not list themselves. But if it is not in the catalog, then it fits the rule and must be included. Just like with the Barber, we get a logical contradiction. Russell's discovery had major effects on the foundations of mathematics. At the time, many mathematicians believed that sets clearly defined without issues. But Russell showed that some definitions lead to contradictions. His work led to efforts to fix these problems and create a more solid foundation for logic and mathematics. Similar paradoxes appear in everyday life. Consider a sign that reads, "Ignore this sign." If you follow the instruction, you must ignore it, but then you are following what it says, which means you are not ignoring it. This loop of contradiction is like the Barber's paradox. It creates a situation where neither option works. Another common example is the statement, "This sentence is false." If the statement is true, then it must be false, as it claims. But if it is false, then it must be true. There is no way to assign a clear truth value to it. These kinds of self-referential statements lead to paradoxes, because they create logical loops that cannot be resolved. The Barber's paradox also raises interesting questions about rules and definitions. In real life, definitions are usually flexible. If there were an actual barber in a town with this rule, people would likely adjust it to avoid the problem. Perhaps the barber simply decides on a case-by-case basis whom to shave. But when we try to create strict, rule-based systems, paradoxes like this can emerge. This is why careful thinking is important in philosophy, mathematics, and even law. If a law were written in a way that led to contradictions, it could cause problems in court. If a computer program had rules that created logical loops, it could crash. In artificial intelligence, designing rules that avoid contradictions is a major challenge. Self-referential problems, where a system refers to itself, often lead to unexpected errors. One famous example in computing is the halting problem, discovered by Alan Turing. He proved that there is no general way to determine if a given computer program will run forever or eventually stop. If you try to build a program that checks this, it runs into contradictions similar to the Barber's paradox. It leads to a loop where no clear answer is possible. These paradoxes also show the limits of logic. Humans often deal with vague or flexible concepts. In real life, if a barber had this rule, he might just decide to shave or not based on his own preference. But strict logical systems do not allow for flexibility. That is why paradoxes appear when rules are applied too rigidly. A practical example of this problem occurs in bureaucracy. Imagine a company policy that says, all requests must be approved by a manager who does not approve their own requests. What happens if the manager needs to submit a request? There is no higher authority to approve it, yet they are not allowed to approve their own. This creates a deadlock, much like the Barber's paradox. Even in social situations, similar contradictions arise. Imagine a club where the only rule is that members cannot invite themselves. Every new member must be invited by an existing member. If the club starts with no members, it can never have members because no one is allowed to invite themselves. This is another case where a strict rule leads to an impossible situation. Paradoxes like these help us think more carefully about definitions and systems. They show that not all problems have clear solutions. They also remind us that language and logic have limits. Sometimes, the way a question is framed makes it impossible to answer. Recognizing these issues helps us avoid making incorrect assumptions. The Barber's paradox is a simple example of a deep logical problem. It teaches that rules must be carefully designed to avoid contradictions. It also connects to larger issues in mathematics, computer science, and philosophy. While no real barber faces this exact problem, the paradox serves as a useful thought experiment. It shows that strict classifications sometimes fail, and that self-referential statements can lead to contradictions. Thinking about these issues helps us understand the structure of logic and the challenges of building consistent systems. Cantor's paradox comes from the idea that some infinities are larger than others. This might seem strange at first, because infinity means something that goes on forever. But when dealing with infinite sets in mathematics, there are different sizes of infinity. This paradox appears when thinking about the power set of an infinite set. The power set is the set of all subsets of a given set, including both the empty set and the full set itself. Cantor showed that the power set of any set, whether finite or infinite, is always strictly larger than the original set. This creates a paradox when applied to the set of all sets. To understand this, first think about how counting works. In the world of finite numbers, comparing sizes is easy. A set with 5 elements is smaller than a set with 10 elements, but in the case of infinite sets, comparing sizes is more complicated. The natural numbers, which include all whole numbers starting from 1, form an infinite set. It might seem that this is the biggest infinity possible, but it is not. Cantor discovered that not all infinities are equal. He proved that the set of real numbers, which includes all numbers with decimal places, is a larger infinity than the set of natural numbers. This result is surprising because it shows that some infinite sets have more elements than others, even though both go on forever. He demonstrated this using a method called diagonalization, which proves that any attempt to list all real numbers will always miss some. Now consider the power set, which is the set of all subsets of a given set. If the original set has 3 elements, its power set includes 8 subsets. If a set has 4 elements, its power set contains 16 subsets. This pattern continues, and the number of subsets grows exponentially. For an infinite set like the natural numbers, the power set is even larger. Cantor proved that the power set of an infinite set always has a strictly larger size than the original set. The paradox appears when thinking about the set of all sets. If such a set exists, then it must have a power set. But the power set is always larger than the original set. This means the set of all sets must be smaller than its own power set, which contradicts the idea that it contains everything. This contradiction shows that the concept of a set of all sets is not logically possible within standard set theory. One way to grasp this is to consider an analogy. Imagine a library with an infinite number of books. Each book represents a number in an infinite set. Now imagine creating a second library where each book represents a different combination of books from the first library. This second library will always be larger than the first. No matter how large the first library is, the second will always contain more books. The power set acts in the same way, always producing a larger infinity. Cantor's work led to important developments in mathematics, especially in set theory. His discoveries forced mathematicians to rethink the nature of infinity. Before his work, many people assumed that infinity was a single concept, but he showed that there are different levels of infinity, each larger than the one before. His results also led to the creation of new logical frameworks to handle these paradoxes. The paradox also influenced the foundations of mathematics. It helped reveal inconsistencies in early set theory, leading to refinements such as Zermelo-Fraenkel set theory. This system avoids the paradox by restricting how sets can be formed. It does not allow a set of all sets, which prevents the contradiction from arising. In everyday life, infinity usually appears in a vague way, such as when people talk about something lasting forever. But in mathematics, infinity has precise meanings. Understanding different sizes of infinity has applications in logic, computer science, and even physics. For example, the concept of different infinities appears in discussions about the structure of the universe and the nature of space-time. Many people struggle with the idea that one infinity can be larger than another. It goes against intuition, but examples help clarify the concept. Consider a hotel with an infinite number of rooms. If every room is occupied, it might seem that no more guests can be added, but if every guest moves to the next room, the first room becomes available. This shows that infinity behaves differently from finite numbers. Now imagine a hotel with an even larger infinity, where each room number represents a real number instead of a whole number. No rearrangement of guests in the first hotel can ever fill this second hotel. This illustrates the difference between different infinities. Cantor's paradox shows that infinity is not a single, simple idea. It has structure and complexity. The discovery that power sets always create a larger infinity than the original set led to deep insights in mathematics. The paradox itself is not a flaw in logic, but a sign that set theory needed more careful definitions. This led to improvements that form the foundation of modern mathematics. Understanding this paradox requires letting go of common assumptions about numbers and size. It challenges the way people think about counting and comparing quantities. Cantor's work changed mathematics forever, introducing new ways to think about the infinite. While his discoveries were controversial at first, they are now a fundamental part of mathematical theory. The Berry paradox arises when we try to describe numbers using words. It starts with a simple idea. Some numbers can be described in fewer words than others. For example, 100 takes only 2 words, while the smallest number greater than 1,000,000 takes 7. In everyday language, we often define numbers this way without issue. However, trouble appears when we consider the phrase, the smallest number not definable in under 11 words. At first, this seems like a valid description, but a contradiction emerges. The phrase itself has only 10 words, which means it defines the number it claims cannot be defined in under 11 words. This paradox challenges how we think about definitions, language, and logic. It was named after G.G. Berry, a British librarian, and was popularized by Bertrand Russell, who was deeply interested in logical problems. The issue at its core is self-reference. The definition refers to itself in a way that creates a loop, leading to a contradiction. To understand why this is a problem, consider a simpler example. Suppose someone tells you, this statement is false. If the statement is true, then it must be false as it claims. But if it is false, that means it must be true. There is no consistent way to resolve this without contradiction. The Berry paradox works similarly. It uses a phrase that appears to define a number, but by doing so, it contradicts itself. Imagine a dictionary listing numbers by their descriptions. Each entry must follow a rule. The description must be shorter than the number itself when written out. The number 15 is easy. It takes only 1 word. But now, imagine searching for the smallest number that needs more than 10 words to define. If you find such a number and describe it using fewer words, the definition no longer works because the number does not actually need more than 10 words anymore. The paradox reveals a problem with how we use language to define things. One key issue is vagueness. Words like definable seem clear, but can become tricky when applied to the whole set of numbers. Definitions rely on rules, but natural language does not always follow strict rules. Mathematical definitions try to avoid vagueness, yet even they run into problems when dealing with self-reference. This paradox has deep implications in mathematics and logic. It relates to problems discovered by Kurt Gödel in his incompleteness theorems. Gödel showed that any system of mathematics rich enough to describe numbers must contain statements that are true but cannot be proven within the system. This is similar to the Berry paradox because both involve statements that refer to themselves in ways that cause contradictions. To see why definitions matter, consider how we describe everyday objects. Suppose you are at a lost and found office looking for your umbrella. If you say, "I lost a black umbrella," you have defined an object clearly enough for someone to help you find it. But if you say, "I lost the umbrella that cannot be described in fewer than 10 words, the staff would be confused. The description defeats itself because it does not specify what makes the umbrella unique. The paradox also connects to problems in computing. In programming, we use functions to define tasks. If a function were written to search for the shortest program that cannot be written in fewer than 11 lines, it would run into the same contradiction as the Berry paradox. If the program finds such a function and writes it in fewer lines, then the function was not truly necessary. This problem is related to the field of algorithmic information theory, which studies the limits of what can be computed. Some might think the paradox is just a word trick. However, it exposes real issues in logic. The problem is not with the number itself, but with how we describe numbers. It shows that our ability to describe things using words is limited by the structure of language. Words depend on meanings that can change based on context, and this flexibility leads to contradictions when pushed to extremes. A similar issue appears in law and philosophy. Consider a law that states, all laws must be followed unless they contradict themselves. If such a law exists, what happens if a law contradicts itself? Should it be followed or ignored? The same circular reasoning occurs in the Berry paradox. where the definition includes a condition that contradicts itself when applied. Another example appears in competitions. Suppose a judge announces a prize for the shortest poem that cannot be described in fewer than 10 words. If a poet submits a poem and the judge accepts it, then it must have been describable in fewer than 10 words, contradicting the contest rules. If no poem fits, then the contest rule itself cannot be applied. Paradoxes like this remind us to be careful with definitions. In everyday life, we rarely face such contradictions, but they become important in logic, law, and computer science. They show that language, while powerful, has limits when dealing with self-reference and meaning. Mathematicians avoid these problems by using precise formal systems. Instead of using words, they define numbers using symbols and strict rules. However, even formal systems must be designed carefully to avoid contradictions. The Berry paradox suggests that any attempt to fully capture the concept of definable numbers in a formal way may run into fundamental limits. This paradox also highlights the difference between human intuition and strict logic. Most people understand numbers in a practical way without needing formal definitions. However, when pushed to the limits of logic, even simple ideas can lead to unexpected contradictions. It is a reminder that language, while useful, is not perfect when describing complex ideas. In summary, the Berry paradox shows how self-referential definitions create contradictions. It is based on the idea that some numbers require long descriptions while others do not. The problem occurs when we try to define the first number that needs more than 10 words in fewer than 10 words. This creates a logical loop that cannot be resolved. The paradox appears in many areas, including mathematics, computing, law, and philosophy. It teaches us about the limits of language and logic, reminding us to think carefully about how we define things. Richard's paradox is a problem in mathematics that arises when using language to describe numbers. It shows how a contradiction can appear when trying to classify numbers using words. The paradox involves self-referential descriptions, meaning definitions that refer to themselves in some way. To understand the paradox, think about how numbers can be described in words. Some numbers have simple descriptions. The number 1 can be described as the first positive whole number. The number 100 can be described as 10 squared. Even more complex numbers can be described in words. For example, pi can be called the ratio of a circle's circumference to its diameter. Any number that can be uniquely defined using a finite number of words in English is considered a definable number. Now, consider the set of all numbers that can be defined using a sentence in English with fewer than 20 words. This set includes many numbers like 1, 2, and 3, as well as more complicated ones like the square root of 2. Since there are only a finite number of words in English and a finite number of ways to arrange them into sentences of a fixed length, this means there must be only a countable number of such definable numbers. But the set of real numbers is uncountable. This means that most real numbers cannot be described in a finite number of words. They exist, but there is no way to specify them exactly using language. Now comes the paradox. Consider the phrase, the smallest number that cannot be defined in fewer than 20 words. This phrase itself has only 18 words. If it refers to a real number, then that number must be definable in English using this sentence. But by definition, it is not supposed to be definable in fewer than 20 words. That creates a contradiction. This paradox is similar to other self-referential problems in logic. It works because of a trap in language. The phrase pretends to refer to a number that is not definable in a short sentence, but the sentence itself provides that definition. That means the number must be definable, contradicting the original claim. This is a fundamental problem when trying to use natural language to precisely describe mathematical objects. A similar paradox happens when thinking about numbers that are described in indirect ways. Imagine listing all numbers that can be defined in English using a sentence of 10 words or fewer. This list might include 0, 1, a few fractions, some irrational numbers, and other well-known values. Since there are only so many possible sentences, this list must be finite. But what about the phrase, the smallest number not in the list above? If this number exists, then it is defined by that phrase, which has fewer than 10 words. That means it should have been in the list, but it was explicitly defined as the smallest number not in the list. That contradiction is at the heart of Richard's paradox. This paradox does not just apply to English. It applies to any system that uses a finite set of symbols to describe numbers. The problem arises because language allows definitions that indirectly refer to things that supposedly cannot be referred to. The contradiction comes from treating descriptions as if they work like numbers themselves. Numbers exist independently of language, but descriptions depend on the structure of the language used. A related paradox appears in the idea of self-referential statements. The most famous example is the liar paradox, which comes from the sentence, "This sentence is false." If the sentence is true, then it must be false. But if it is false, then it must be true. The contradiction arises because the sentence refers to itself in a way that breaks logical consistency. Richard's paradox works in a similar way. It creates a description that tries to exist inside and outside of a definable set at the same time. Mathematicians and logicians use this paradox to show the limits of formal definitions. One way to resolve the paradox is to say that certain definitions are invalid. Just because a phrase follows the rules of grammar does not mean it corresponds to a well-defined mathematical object. This approach suggests that language is not always reliable when describing infinite sets like real numbers. Another way to handle the paradox is through formal logic. In formal systems, definitions must follow strict rules to avoid self-reference problems. This is similar to how computer programs must be written carefully to avoid infinite loops. In mathematics, systems like Zermelo-Fraenkel set theory and Gödel's incompleteness theorems help define what kinds of statements can be formally valid. Gödel's work, in particular, showed that in any sufficiently complex mathematical system, there will always be true statements that cannot be formally proven within that system. This idea is closely related to the paradox. The paradox also has connections to information theory. If a number can be described using a finite sentence, then that means it contains only a limited amount of information. But most real numbers require an infinite amount of information to be described exactly. These numbers are truly random in a sense. There is no pattern or rule that can describe them completely in a finite way. Richard's paradox highlights the strange boundary between numbers that can be named and numbers that cannot. This paradox also appears in discussions of artificial intelligence and machine learning. If an AI tries to define all possible concepts using natural language, it may run into contradictions like this. Some concepts might seem to be describable, but their definitions might collapse under closer examination. This shows a fundamental challenge in creating systems that understand meaning precisely. Thinking about this paradox can help clarify the difference between descriptions and objects. Numbers exist regardless of whether we describe them, but our ability to describe them depends on the structure of language. The paradox emerges when we assume that language and numbers behave in the same way. Understanding where this assumption breaks down helps reveal the limits of formal reasoning. A useful way to explore this paradox is by trying to define numbers in different ways. Consider how many words it takes to describe simple numbers like 1, 2, and 3. Then try describing larger numbers like 1 million or 1 Google. As numbers grow larger, their descriptions tend to grow as well. But at some point, it becomes impossible to define certain numbers concisely. This happens even though those numbers still exist in the number line. Thinking about the paradox also helps when considering real-world situations where definitions matter. In law, philosophy, and science, definitions often shape how concepts are understood. But if a definition is self-referential or contradictory, it can create confusion. This is why clear and precise definitions are important in fields that rely on logic and reasoning. Richard's paradox does not mean mathematics is flawed, but it does show the limits of certain ways of thinking. It teaches that not every phrase that looks like a definition actually defines something. It also demonstrates that language can create illusions of meaning where none exists. By studying the paradox, mathematicians and logicians gain a better understanding of how to avoid contradictions in formal systems. Even though the paradox is subtle, it has deep implications. It connects to fundamental ideas in logic, computation, and philosophy. It shows that not everything can be neatly categorized. Some things, including most real numbers, exist beyond the reach of language. Recognizing these limits helps build a clearer understanding of the nature of mathematics and the way we use language to describe the world. The Grelling-Nelson Paradox is a puzzle about words and how they describe themselves. It asks whether the word heterological is heterological. The question seems simple, but when examined closely, it leads to a contradiction. To understand the paradox, first consider how words describe themselves. Some words have a property that applies to them. For example, the word short is short. The word English is an English word. These words are called autological because they describe themselves. On the other hand, words that do not describe themselves are called heterological. For example, the word long is not long. The word French is not a French word. These words do not have the property they describe, so they are heterological. Now consider the word heterological itself. By definition, a heterological word does not describe itself. So, is heterological heterological? If it is, then it does not describe itself. But the definition of heterological is that it does not describe itself. So that means it must be heterological. That seems correct at first. However, the problem appears when considering the other possibility. If heterological is not heterological, then it must be autological. That means it must describe itself. But the definition of heterological is that it does not describe itself. So if it describes itself, it must not be heterological. That creates a contradiction. It cannot be both heterological and not heterological at the same time. This is the paradox. The issue is similar to the famous liar paradox, where someone says, "I am lying." If they are telling the truth, then they must be lying. But if they are lying, then they must be telling the truth. This self-referential loop causes the contradiction. The Grelling-Nelson Paradox does the same thing with word classification. To see the paradox more clearly, imagine a list of words divided into two categories, autological and heterological. The autological list contains words that describe themselves, while the heterological list contains words that do not. Most words fit neatly into one of these groups. But when trying to place heterological, a problem arises. If it belongs in the heterological list, then by definition, it does not describe itself, which means it should be there. But if it is in that list, it describes itself as not describing itself, which makes it autological. If placed in the autological list, it should describe itself, but its definition means it cannot. A way to explore this paradox further is to apply it to other concepts. Consider categories that define themselves. The category of abstract ideas is an abstract idea. The category of things that are not words is not a word. But what about the category of things that do not fit into their own category? If it fits, it does not fit. If it does not fit, it fits. This mirrors the paradox of heterological. In logic, self-referential problems like this often point to deeper issues with definitions and language. Mathematicians and philosophers have struggled with similar paradoxes when dealing with set theory and logic. Bertrand Russell encountered a similar issue when considering the set of all sets that do not contain themselves. If such a set exists, does it contain itself? If it does, then it should not. If it does not, then it should. This led to Russell's paradox, which influenced the foundations of mathematics. The Grelling-Nelson Paradox highlights the limits of how language describes itself. It shows that certain words or concepts cannot be classified without leading to contradictions. Some have tried to resolve the paradox by refining the definition of heterological. One approach is to restrict the definition to avoid self-reference. Another is to accept that some words cannot be classified in a straightforward way. These solutions attempt to avoid the contradiction, but they do not eliminate the deeper issue of self-reference. This paradox also raises questions about whether all words can be neatly categorized. Language is flexible, and meanings shift based on context. Some words change their classification depending on how they are used. A word might be autological in one situation and heterological in another. For example, the word printed is printed when written on a page, but not when spoken aloud. This fluidity suggests that language does not always follow strict logical rules. Philosophers have debated whether paradoxes like this reveal flaws in human reasoning or just limitations in language. Some argue that paradoxes arise when people assume language works like mathematics. In math, definitions are precise and unambiguous. In language, meanings depend on usage and interpretation. This difference means that some paradoxes may not need solutions, but instead serve as reminders that words are tools, not fixed entities. One way to avoid the paradox is to reject the idea that all words must fit into only one category. Instead of forcing heterological to be either autological or heterological, consider that some words do not fit neatly into any category. This avoids contradiction by acknowledging that some concepts defy simple classification. However, this solution may feel unsatisfying because it does not resolve the paradox, it only sidesteps it. The paradox also has implications beyond language. It appears in logic, mathematics, and even philosophy. Whenever a system tries to define itself, contradictions can arise. This is why self-referential problems appear in many fields. In computer science, self-referential loops can cause infinite loops in programs. In law, rules that apply to themselves can lead to conflicts. In philosophy, self-reflection can create paradoxes about identity and knowledge. The Grelling-Nelson Paradox may seem like a word game, but it connects to deep questions about classification, logic, and meaning. It challenges the assumption that everything can be neatly defined. It also serves as a reminder that words are not always as clear-cut as they seem. Language is a powerful tool, but it has limits. Some concepts resist simple categorization, and forcing them into rigid definitions can create problems. This paradox also shows why definitions matter. In everyday life, people often use words without thinking about their exact meanings. But in logic and philosophy, definitions must be precise to avoid contradictions. The Grelling-Nelson Paradox demonstrates what happens when a definition turns back on itself. It reveals the hidden complexity in something as simple as classifying words. While the paradox does not have a straightforward solution, it provides insight into how language works. It reminds us that some questions do not have clear answers. It also highlights the importance of careful thinking when dealing with self-referential ideas. Whether in mathematics, philosophy, or everyday reasoning, understanding the limits of language helps avoid confusion and paradoxical traps. Even though the paradox remains unsolved, it continues to spark discussion and debate. It challenges assumptions and encourages deeper thinking about how words relate to the concepts they describe. It is a small puzzle with broad implications, showing that even the simplest questions can lead to profound insights. Zeno's paradoxes challenge how people understand motion and time. They suggest that movement, which seems obvious, may not be possible at all. These paradoxes come from the Greek philosopher Zeno of Elea, who lived in the 5th century BCE. He created them to support the ideas of his teacher, Parmenides, who argued that change and motion are illusions. The paradoxes have puzzled mathematicians and philosophers for centuries. One of the most famous paradoxes is Achilles and the tortoise. In this thought experiment, the great warrior Achilles races a tortoise. Since Achilles is much faster, the tortoise gets a head start. Zeno argues that Achilles can never catch the tortoise. First, he must reach the spot where the tortoise started. By then, the tortoise has moved ahead. When Achilles reaches that new spot, the tortoise has moved again. This pattern continues infinitely, always leaving Achilles with more distance to cover. The conclusion seems absurd because, in real life, Achilles easily overtakes the tortoise. Yet the logic of the paradox suggests otherwise. Another paradox, called the Dichotomy Paradox, questions whether anyone can reach a destination. To walk from one place to another, a person must first reach the halfway point. Before that, they must reach the quarter point. Before that, they must travel 1/8 of the way, and so on. This process divides the journey into an infinite number of steps. If every step takes time, then covering an infinite number of steps should take infinite time. That suggests no one can ever move at all. Yet people walk, run, and drive every day without trouble. The arrow paradox explores motion in a different way. Zeno asks people to imagine an arrow flying through the air. At any single moment, the arrow is in one position. In that moment, it does not move forward or backward. If time is made of individual moments, and in each moment the arrow does not move, then it should never move at all. The paradox argues that motion is impossible because at every instant the arrow is still. A fourth paradox, the stadium paradox, involves three sets of moving objects. Zeno describes two rows of runners moving in opposite directions past a stationary row of runners. Depending on how someone measures their movement, the moving runners seem to travel twice as fast or half as fast as expected. The paradox suggests contradictions in how people measure time and space. These paradoxes raise important questions about motion and continuity. They challenge assumptions about how space and time work. The paradoxes do not mean that motion is actually impossible. Instead, they reveal gaps in how people think about movement. Mathematicians eventually found solutions using modern tools like calculus and limits. Achilles and the tortoise relies on the idea of infinite sums. When adding smaller and smaller distances, the total sum approaches a finite limit. Achilles does catch the tortoise because the infinite steps take only a finite amount of time. The dichotomy paradox also breaks down using the same logic. The infinite steps shrink in size, and their total sum is finite. A person can reach a destination because an infinite sequence can still have a finite result. The arrow paradox is more about how time is viewed. If time is continuous rather than made of still moments, the problem disappears. The arrow moves smoothly rather than jumping between frozen positions. The stadium paradox relates to relative motion. Different observers measure speeds differently, depending on their point of view. Modern physics handles such cases using relativity, but the paradox highlights how assumptions about measurement can lead to confusion. Beyond math and physics, Zeno's paradoxes still influence modern thought. They appear in philosophy, where people debate whether time and space are continuous or made of tiny parts. The paradoxes also affect discussions in computer science, where algorithms sometimes rely on infinite processes that must still finish in finite time. These paradoxes remain valuable because they force people to question what seems obvious. They show how logical reasoning can lead to strange conclusions, even about something as basic as motion. They remind people to examine their assumptions and think carefully about concepts that may seem simple at first. The Monty Paradox is a problem that confuses many people. It comes from a game show where a contestant must pick between three doors. Behind one door is a car. Behind the other two doors are goats. The contestant picks a door but does not open it. Then the host, Monty Hall, who knows what is behind each door, opens a different door to reveal a goat. The contestant now has a choice. They can stick with their original pick or switch to the remaining closed door. Most people assume that it does not matter whether they switch or stay. They believe each door has a 50-50 chance of hiding the car. This is incorrect. Switching actually doubles the chance of winning. To understand why, think about the contestant's first choice. There are three doors, and only one has the car. That means the chance of picking the car on the first try is 1 out of 3. The chance of picking a goat is 2 out of 3. When Monty opens a door, he does not do so randomly. He always picks a door with a goat. That provides information. If the contestant originally picked a goat, switching will lead to the car. If the contestant originally picked the car, switching will lead to a goat. Since the first choice had a 2/3 chance of being a goat, switching wins 2/3 of the time. Imagine playing the game with 100 doors instead of 3. There is still one car, but now there are 99 goats. The contestant picks one door. The chance of picking the car is 1 out of 100. The chance of picking a goat is 99 out of 100. Now Monty opens 98 other doors, all showing goats. That leaves only one unopened door besides the contestant's choice. It is easy to see that the remaining closed door almost certainly has the car. The same logic applies to the original 3-door version, just on a smaller scale. Many people find this answer hard to accept. It feels wrong. They test it by playing many times, tracking how often switching wins versus staying. Over a large number of rounds, switching wins about 2/3 of the time, while staying wins only 1/3. This proves the math and shows that intuition can be misleading in probability. The paradox became famous when Marilyn Vos Savant wrote about it in a magazine. She explained the correct answer, but many readers disagreed. Even some mathematicians wrote in to argue. They believed that after Monty opened a door, there were 2 remaining choices, so the odds must be equal. But they made a mistake. They forgot that Monty does not pick his door randomly. He always picks a door with a goat. His choice is based on knowledge. That changes the probabilities. Some people still think the choice resets after Monty opens a door. They believe that because 2 doors remain, the game starts over with equal odds. That is not true. The original 1 in 3 probability does not change. The remaining door must take the probability that was lost when Monty removed an option. This paradox teaches an important lesson about probability. It shows how probabilities change when new information is available. It also reveals how human intuition about chance can be wrong. Many probability problems seem simple but have unexpected answers. That is why even experienced mathematicians sometimes struggle with them. This type of thinking applies in other situations. In medicine, tests for rare diseases give an example. Suppose a disease affects only 1 in 1,000 people. A test for the disease is 99% accurate. Someone who tests positive might think they have a 99% chance of having the disease. But that is not true. Since the disease is rare, most positive test results are false alarms. Understanding probability correctly helps doctors and patients make better decisions. A similar issue happens in gambling. Many people believe in lucky streaks. If a roulette wheel lands on black several times in a row, gamblers often think red is more likely next. But each spin is independent. The past does not affect future results. The Monty Hall problem is different because Monty's choice is not independent. He acts with knowledge, which changes the odds. Some versions of the problem change the rules. What if Monty does not always open a door? What if he sometimes picks randomly? These variations affect the outcome. But in the standard version, the math is clear. Switching is the best choice. The Monty Hall Paradox also appears in real life outside of games. Imagine a company choosing between 3 job candidates. The employer prefers one but cannot decide. They eliminate one candidate for a minor reason. Now there are 2 left. The choice feels even, but it is not. The employer originally had a stronger preference for one. The Monty Hall effect suggests that when forced to reevaluate a decision, people should consider switching. Many people learn best by seeing results. The easiest way to believe the Monty Hall answer is to test it. Playing the game multiple times reveals the truth. Switching wins more often than staying. This simple experiment convinces most skeptics. The Monty Hall Paradox shows that probability is not always intuitive. It reminds people to think carefully about chance, evidence, and decision-making. The lesson applies in many areas, from business to medicine to everyday choices. Sometimes the best answer is the one that feels least obvious. The Sleeping Beauty problem is a thought experiment that challenges how people think about probability and belief updating. It involves a simple setup, but leads to a surprising debate. The question seems straightforward, yet experts disagree on the answer. Imagine a researcher tells Sleeping Beauty that she will participate in an experiment. The rules are clear. On Sunday, she will go to sleep. A fair coin will be flipped. If the coin lands on heads, she will be woken up on Monday, asked a question, and then put back to sleep. If the coin lands on tails, she will be woken up on Monday, asked the same question, put back to sleep, and woken up again on Tuesday. Each time she wakes, she will not remember whether she has woken before. The researcher will always ask her the same question: what is your belief that the coin landed on heads? At first, this seems like a basic probability question. A fair coin has a 1/2 chance of landing on heads and a 1/2 chance of landing on tails. If Sleeping Beauty were asked on Sunday before the experiment started, she would confidently say 1/2. But when she wakes up inside the experiment, things are different. She does not know whether it is Monday or Tuesday. She knows that if the coin landed on tails, she will wake up twice. This changes the way she should think about probabilities. 2 common answers arise from this setup. The first answer is 1/2. This view, called the halfer position, argues that nothing has changed from the original coin flip. When Sleeping Beauty wakes up, she gains no new information about the coin. The probability of heads remains 1/2, just as it was before she went to sleep. Supporters of this view say that waking up does not count as evidence because it was expected in both cases. The second answer is 1/3. This view, called the thirder position, argues that Sleeping Beauty must consider all the times she could wake up. There are 3 possible wake-up moments: Monday if the coin is heads, Monday if the coin is tails, and Tuesday if the coin is tails. Since the tails scenario involves 2 awakenings, and each waking moment is equally likely from her perspective, she should assign 1/3 to heads and 2/3 to tails. Supporters of this view say that the key to the problem is that Sleeping Beauty does not just care about the coin flip, but also about when she is awake. This debate highlights how probability depends on how information is framed. The Hafer view treats the coin flip as the key event. The thirder view treats each wake-up moment as the key event. Neither approach is obviously wrong, which is why this problem remains controversial. A useful way to think about it is to compare it to similar problems. Suppose a person plays a lottery where they get 2 tickets instead of 1, but they do not remember whether they bought 1 ticket or 2. If they wake up knowing they are in the game, should they believe they had a single ticket or 2? Since the 2-ticket scenario doubles the chance of waking up, the reasoning matches the thirder argument. Another comparison is with a bet. Suppose Sleeping Beauty is offered a bet where she wins $1 if the coin lands on heads, but loses $2 if the coin lands on tails. If she follows the 1/2 probability, she expects to break even, since she wins $1 half the time and loses $2 half the time. But if she follows the 1/3 probability, she expects to lose on average because she will lose twice as often as she wins. In a repeated game, a thirder would avoid this bet, while a halfer might accept it. This problem connects to real-world ideas in probability, philosophy, and decision theory. In science, experiments often involve multiple observations, and how people count those observations affects the conclusions. In psychology, memory loss or incomplete information can lead to similar puzzles. In economics, decisions often depend on how outcomes are framed, just like in the Sleeping Beauty problem. The paradox also ties into ideas about self-location. When Sleeping Beauty wakes up, she knows she exists, but she does not know which moment she is experiencing. This makes it different from ordinary probability questions. Normally, when someone flips a coin, they can check the result. Here, Sleeping Beauty cannot check whether it is Monday or Tuesday, which changes how she should reason. The problem has been studied in philosophy and mathematics, with arguments on both sides. Some people try to resolve the debate by focusing on formal probability rules. Others argue that it depends on how probability is interpreted. Frequentists, who define probability based on long-run frequencies, often lean toward 1/3 because in repeated experiments, 2/3 of wake-ups happen in the tails case. Bayesians, who update beliefs based on new evidence, can argue for either position depending on how they define evidence. One reason the problem remains unsettled is that different ways of thinking about probability lead to different answers. If probability means chance before knowing anything, then 1/2 makes sense. If probability means chance given that I am awake, then 1/3 makes sense. Since both interpretations are reasonable, the paradox continues. Some extensions of the problem explore what happens if Sleeping Beauty knows the day of the week, or if the experiment is changed to wake her up more times on tails. These variations show that the core issue is how people count events and update their beliefs. The Sleeping Beauty problem remains one of the most debated paradoxes in probability. It challenges people to think carefully about what probability means and how beliefs change with new information. The answer depends on perspective, making it a valuable problem for understanding reasoning and uncertainty. The boy or girl paradox is a probability puzzle that seems simple but leads to counterintuitive results. It starts with a basic question. If a family has 2 children, and we know at least one is a boy, what is the probability that the other child is also a boy? Many people assume the answer is 50% because there are 2 possibilities. The other child is either a boy or a girl, but the actual probability depends on how the information was given. To see why, start by listing all the possible combinations of 2 children. There are 4 equally likely possibilities: an older boy and a younger boy, an older boy and a younger girl, an older girl and a younger boy, or an older girl and a younger girl. If we assume each child has an equal chance of being a boy or a girl, then these combinations occur with equal probability. But the key detail is that we already know at least one child is a boy. That means the combination where both children are girls is ruled out. Now only 3 possibilities remain: boy-boy, boy-girl, and girl-boy. Since each of these was originally equally likely, removing one does not change the probabilities of the others. That means the chance of having a boy and a girl is twice as high as having 2 boys. In other words, the correct probability that both children are boys is 1 in 3, not 1 in 2. This result surprises people because it seems like a simple counting problem. But the key is to recognize that probabilities must be updated based on new information. The way the information is presented changes the answer. If instead we were told that a specific child, such as the older one, is a boy, then the probability of both being boys would indeed be 1 in 2. In this case, only 2 combinations remain: boy-boy and boy-girl. Each is equally likely, so the probability of both being boys is 50%. The paradox arises because the problem does not specify how the information was obtained. If someone randomly selects a child and finds out it is a boy, that is different from learning only that there is at least one boy in the family. The 2 methods give different probabilities. This subtle difference is why many people get the answer wrong. To make this clearer, consider a real-world example. Imagine a large group of families, each with 2 children. In one version of the problem, we go through every family and pick one child at random. If that child is a boy, we then ask what the chance is that the other child is also a boy. In this case, half the time the second child will be a boy, and half the time the second child will be a girl. That gives a probability of 50%. But in the original version of the paradox, we do not pick a child at random. Instead, we ask only whether the family has at least one boy. If the answer is yes, we then calculate the probability of 2 boys. This difference matters because it changes which families are included in the calculation. By removing the families with 2 girls, we alter the original probability distribution. This idea of conditional probability appears in many real-world situations. In medical testing, for example, the probability of having a disease given a positive test result is not the same as the probability of testing positive given that someone has the disease. This misunderstanding leads people to overestimate the accuracy of medical tests. If a test is 95% accurate, but the disease is rare, most positive results will actually be false positives. The same principle applies to criminal investigations. Suppose a fingerprint found at a crime scene matches a suspect's fingerprint. Many people assume this means the suspect is very likely guilty, but that depends on how many people could match the fingerprint. If millions of people could match, then the probability of guilt is much lower than it seems at first. The boy or girl paradox is also related to the Monty Hall problem. In both cases, people assume equal probabilities when they should update their beliefs based on new information. The paradox teaches that the way a question is asked affects the answer. In probability, small details can make a big difference. A useful way to test the paradox is to simulate it. Suppose we look at 1,000 families, each with 2 children. About 250 families will have 2 boys, 500 will have 1 boy and 1 girl, and 250 will have 2 girls. If we remove the families with 2 girls, we are left with 750 families. Out of those, only 250 have 2 boys. That means the probability of both children being boys is 1 in 3. Another way to think about it is through betting. If someone offers a bet on whether the second child is a boy, a person who assumes a 50% chance will lose money over time. But a person who understands the correct probability will bet accordingly and win in the long run. This shows that probability is not just an abstract idea, but has real consequences. Some people still argue that the answer should be 50% because they think of probability in terms of individual cases rather than groups. They imagine a single family and believe that since the second child could be either a boy or a girl, the chance must be equal. But probability does not work that way. It applies to repeated trials and groups, not just individual events. This paradox also appears in genetics. If a couple carries a gene for a recessive disease, the chance of passing it to a child depends on whether the child inherited 1 or 2 copies of the gene. If a family already has one affected child, the probability of another affected child is not always the same as for the first child. Doctors use conditional probability to calculate risk in genetic counseling. The lesson from the boy or girl paradox is that probability is not always intuitive. People tend to think in terms of simple ratios, but real-world probabilities depend on context. Understanding how information affects probability helps in everyday decisions, from medical choices to financial planning. One of the most important takeaways is that probability is not just about numbers. It is about logic and reasoning. When faced with uncertain situations, people should consider how their knowledge changes the odds. This kind of thinking applies to everything from investing in stocks to understanding risks in daily life. Probability often challenges intuition. The best way to improve at it is to practice with different examples. Many famous paradoxes, like the birthday paradox and the Bertrand paradox, show how probability defies expectations. The boy or girl paradox is just one example of how small changes in wording can lead to big differences in understanding. This problem also connects to artificial intelligence and machine learning. When training models, algorithms must adjust their probabilities based on new data. If they make incorrect assumptions, their predictions will be wrong. The paradox highlights how updating beliefs based on evidence is essential in many fields. Probability problems like this one are not just puzzles. They reveal deeper truths about logic and reasoning. The boy or girl paradox teaches that details matter. It shows that assumptions shape conclusions. It reminds us that common sense is not always correct. By thinking carefully about probability, people can make better decisions in many areas of life. Bertrand's paradox is a problem in probability that shows how defining randomness can lead to different answers. It asks a simple question. If you pick a chord at random inside a circle, what is the probability that the chord is longer than the side of an inscribed equilateral triangle? The answer seems straightforward, but it depends entirely on how you define random. Different ways of choosing the chord lead to different probabilities, which is why the problem is called a paradox. To understand the question, imagine a circle. Inside this circle, an equilateral triangle is drawn so that all three corners touch the edge of the circle. The goal is to pick a chord at random and determine the probability that it is longer than a side of this triangle. The trick lies in how the chord is selected. Since randomness must be defined mathematically, different interpretations lead to different results. One method of selecting a random chord is to pick two random points on the circle's edge and draw a line between them. This seems natural since any 2 points determine a chord. If you do this many times and measure the fraction of chords longer than the triangle's side, the probability is about 1/3. A second method chooses a random point inside the circle as the midpoint of the chord. Then, the chord is drawn so that this midpoint is in the center. If you repeat this process, you get a different probability. Now, the chance that the chord is longer than the triangle's side is 1/2. A third method picks a random point along the radius of the circle. From this point, a chord is drawn perpendicular to the radius. Using this method, the probability that the chord is longer than the triangle's side is 1/4. The paradox exists because each method is logical, yet each gives a different probability. That suggests there is no single correct answer unless the method of choosing the chord is defined first. This contradicts many people's intuition about probability, which often assumes that randomness should lead to a single clear result. To see why different methods give different answers, consider each approach in detail. The first method, picking two random points on the circle, makes every possible chord equally likely. This means chords that cross through the center and shorter chords near the edges are equally probable. Since most randomly chosen pairs of points lead to shorter chords, only about 1/3 of them end up longer than the triangle's side. The second method, using a random midpoint, distributes chords differently. A chord is long when its midpoint is near the center of the circle, and short when the midpoint is close to the edge. Since the midpoint is chosen randomly, there is a 50% chance that it lands within the central region needed for a long chord. This shifts the probability from 1/3 to 1/2. The third method, picking a random point along the radius and drawing a perpendicular chord, gives yet another distribution. In this case, the chord length depends on where the selected point lies. The further it is from the center, the shorter the chord. Since there is a higher chance of selecting a point near the outer edge of the radius than near the center, fewer chords end up being long. That results in a probability of 1/4. Bertrand's paradox is important because it shows that probability can be misleading when randomness is not well defined. In many real-world problems, people assume that picking something at random means a single obvious method exists. This paradox shows that different interpretations of randomness can lead to completely different results. A good analogy is rolling a die. If a fair six-sided die is rolled, the probability of any number appearing is clearly 1/6. But if someone rolls 2 dice and picks the higher number, the probabilities shift. Some numbers now become more likely than others. Similarly, Bertrand's paradox shows that probabilities change based on how the selection process is structured. The paradox has applications beyond mathematics. In physics, defining randomness is crucial in understanding quantum mechanics, thermodynamics, and statistical mechanics. For example, when modeling the movement of particles in a gas, assumptions about how particles interact can drastically change the predicted results. If different ways of defining probability lead to different answers, choosing the right definition becomes critical. In artificial intelligence and computer science, randomness plays a key role in simulations, machine learning, and cryptography. When generating random numbers, it is important to ensure that the method used aligns with the intended application. If randomness is not properly defined, results can be misleading, just as in Bertrand's paradox. This paradox also affects decision-making and statistics. In surveys, how questions are phrased or how samples are selected can change outcomes. If a survey claims to randomly select participants but uses a flawed method, the results may not be truly representative. Bertrand's paradox highlights the importance of carefully defining random processes before drawing conclusions. To resolve the paradox, mathematicians use principles from measure theory and probability distributions. They argue that unless a clear rule for randomness is specified, the question does not have a single correct answer. This means that randomness is not always as simple as it seems. To answer a probability question correctly, one must first define what is being measured and how the selection process works. Understanding Bertrand's paradox helps improve critical thinking about probability and randomness. It challenges assumptions and teaches the importance of precise definitions. In everyday life, people often encounter situations where probability influences decisions, whether in gambling, investing, medical testing, or risk assessment. Recognizing that different methods can lead to different results helps avoid common mistakes in interpreting data. The paradox also shows why intuition about probability is often wrong. Many people assume probabilities should always be obvious and fixed, but this paradox proves that different logical methods can give different probabilities. The lesson is that probability depends on how randomness is framed, not just on the event itself. In summary, Bertrand's paradox reveals how different methods of defining randomness can lead to different results. It appears simple at first, but demonstrates deep mathematical ideas about probability. The paradox teaches the importance of being careful when defining randomness and selecting probability models. It has practical applications in physics, computer science, and decision-making. Most importantly, it reminds us that probability is not just about numbers, but also about how we frame and interpret uncertainty. Simpson's paradox is a statistical phenomenon where a trend appears in different groups of data, but reverses when the groups are combined. This can lead to misleading conclusions. The paradox shows how looking at data in different ways can change the results. To understand how it works, consider a simple example of 2 hospitals, each treating a similar group of patients. Suppose Hospital A has a higher overall survival rate than Hospital B. At first, this suggests that Hospital A provides better care. But when looking at specific groups of patients, the results change. For patients with mild conditions, Hospital B has a higher survival rate. For patients with severe conditions, Hospital B also has a higher survival rate. In both cases, Hospital B seems better, but when all patients are grouped together, Hospital A looks better. How can that happen? The explanation lies in how the patients are distributed. If Hospital A treats mostly mild cases and Hospital B treats mostly severe cases, the overall survival rate will favor Hospital A, even if it performs worse in every category. The numbers alone suggest that Hospital A is better, but the breakdown tells a different story. This paradox often appears in real-world decisions. One well-known case happened in university admissions. A university was accused of gender bias because its overall acceptance rate for men was higher than for women. At first glance, this seemed like discrimination. But when researchers examined individual departments, they found something surprising. In most departments, women had higher acceptance rates than men. The overall difference came from the fact that women applied to more competitive programs with lower acceptance rates, while men applied to less competitive programs. The combined data showed a misleading trend. Another example appears in sports. Suppose two baseball players compete for the best batting average over 2 seasons. In the first season, player A has a higher average than player B. In the second season, player A again has a higher average than player B. But when looking at both seasons combined, player B has the better overall average. This happens because the number of times each player comes to bat affects the totals. If player A performs well in a season where they bat less often and worse in a season where they bat more often, the overall numbers can be misleading. Medical studies often encounter Simpson's paradox. A new drug may seem more effective when tested in 2 separate groups of patients. But when researchers combine the groups, the drug appears less effective. This can happen when different groups of patients have different characteristics, such as age or severity of illness. If younger, healthier patients respond better to treatment and also happen to be overrepresented in one group, the combined results may not reflect the drug's true effect. The paradox also plays a role in economics. Suppose 2 companies raise wages for employees in 2 different job levels. In each job level, one company raises wages by a larger percentage than the other. But when looking at the workforce as a whole, the company that raised wages less in each job level appears to have the higher overall wage increase. This happens because the number of employees at each level affects the total calculation. If a company gives large raises to a few high-paid workers but small raises to many low-paid workers, the average can be misleading. These examples show why Simpson's paradox is important. It reminds people that averages do not always tell the whole story. Decisions based on combined data can be flawed. Researchers, policymakers, and business leaders must be careful when interpreting statistics. They should look at individual groups before drawing conclusions. One way to avoid being misled is to check for hidden variables. These are factors that influence the results, but are not obvious at first. In the hospital example, the severity of a patient's condition is a hidden variable. In the university admissions example, the competitiveness of a department is a hidden variable. Identifying these factors can help people understand what is really happening. Understanding the paradox also helps in everyday life. Imagine 2 coffee shops in town. One shop has an average customer rating of 4.2 stars, while the other has a rating of 4.0 stars. This suggests the first shop is better, but looking at specific ratings shows something different. In the morning, the second shop gets higher ratings. In the evening, it also gets higher ratings. But the first shop has more reviews in the afternoon, when ratings are lower for both shops. This skews the overall average. If someone prefers morning coffee, they should choose the second shop, even though the total rating suggests otherwise. Simpson's paradox is not just a mathematical curiosity. It has serious implications for public policy. Governments use statistics to make decisions on health, education, and crime. If they rely on misleading data, they may implement ineffective policies. For example, crime rates in different neighborhoods might show a decline, but citywide crime appears to be increasing. This can happen if crime decreases in high-crime areas while increasing in low-crime areas. Policymakers who only look at the overall trend may not recognize the true problem. The paradox also affects businesses. A company analyzing customer satisfaction may find that satisfaction is rising in different regions, but falling overall. This could happen if most customers are in a region where satisfaction is lower. If the company only looks at the total numbers, it may misunderstand customer needs. To guard against Simpson's paradox, analysts must break data into meaningful groups. Looking at overall trends is useful, but only if combined with deeper analysis. Businesses, researchers, and governments should ask whether a different grouping of data would lead to a different conclusion. Another lesson from the paradox is the importance of transparency. When organizations present data to the public, they should explain how the data was grouped. Misleading presentations can cause unnecessary concern or false confidence. A news report that shows a decline in graduation rates might overlook that graduation rates actually improved for every major demographic group. A study showing that a medication is ineffective might miss that it works well for a certain age group. One reason Simpson's paradox surprises people is that it goes against intuition. Most people assume that if a trend appears in every group, it must appear in the total data. But the way numbers combine does not always work that way. Percentages and averages can behave differently depending on how the data is divided. The best way to understand the paradox is to test it with real numbers. People who struggle with the concept often find that working through examples helps. A common exercise is to create a fictional hiring scenario where different departments favor one group of applicants, but the overall data tells the opposite story. Seeing how the numbers interact makes the paradox clearer. Simpson's paradox teaches an important lesson about data interpretation. Numbers do not always mean what they seem to mean. Understanding the structure of data is as important as the data itself. Whether analyzing hospital outcomes, university admissions, business performance, or public policy, recognizing the paradox helps people make better decisions. It is a reminder to look deeper and question assumptions before accepting conclusions based on statistics. Borel's paradox is a surprising result in probability theory that involves conditional probability in continuous distributions. It shows that conditioning on an event in a continuous space can lead to different results depending on how the conditioning is done. This paradox challenges intuition and reveals the complexity of working with infinite outcomes. To understand the paradox, imagine a sphere floating in space. A point is chosen at random on the sphere. This means every point has an equal chance of being selected. Now consider the north pole of the sphere. Suppose we condition on the fact that the chosen point lies on the equator. The natural question is, what is the probability distribution of the point along the equator? Intuition suggests that the point should be uniformly distributed along the equator. After all, the original choice of the point was completely random, and the equator is just a slice of that randomness. However, Borel's paradox shows that the answer depends on how we define the conditioning process. One way to condition is to take the original uniform distribution on the sphere and restrict it to the equator. Doing this suggests that the point remains uniformly distributed along the equator. This aligns with common sense. If every point on the sphere was equally likely before, then every point on the equator should remain equally likely after conditioning. But there is another way to approach the problem. Instead of starting with a uniform distribution on the sphere, we can consider a different perspective. Suppose the original point was picked using latitude and longitude. The latitude is chosen randomly, and then the longitude is chosen randomly for a given latitude. If we now condition on the latitude being exactly 0, meaning the point is on the equator, the result is no longer a uniform distribution. Instead, the probability becomes concentrated around certain longitudes depending on how the latitude was chosen in the first place. This is where the paradox arises. The probability distribution along the equator should be the same no matter how we arrived at the condition, but the result changes based on how the conditioning was performed. If we condition in one way, the distribution along the equator is uniform. If we condition another way, the distribution is not uniform. This contradiction seems impossible, but follows directly from the rules of probability. To make this even clearer, think about rolling a fair six-sided die. Suppose we want to know the probability of rolling a 3, given that we rolled an odd number. There are 3 odd numbers, 1, 3, and 5, each equally likely. Given that we rolled an odd number, the probability of rolling a 3 is 1/3. This makes sense because we are just dividing by the number of possibilities that fit the condition. Now imagine that instead of rolling a single die, we roll 2 dice and sum the result. Suppose we condition on the sum being an odd number. Since sums can come from many different pairs of dice, the probability of rolling a certain number changes depending on how the sum was achieved. Unlike the simple case of a single die, different ways of conditioning give different probabilities. This is what happens with Borel's paradox. When conditioning on a continuous event, the way the probability is assigned matters. If one method of conditioning is used, the equator looks uniform. If another method is used, the equator does not look uniform. This reveals a fundamental issue in probability. Conditioning in infinite spaces requires careful handling. The paradox also shows why probability in continuous spaces is more complex than in finite spaces. When dealing with a finite set, conditional probabilities behave predictably, but in an infinite set, the way conditions are applied can change the outcome. This issue appears in many areas of mathematics, especially when working with geometric probability, statistics, and measure theory. A real-world analogy can help illustrate this. Imagine a large crowd spread evenly across a circular stadium. Suppose that instead of looking at the entire crowd, we only consider those standing at a certain distance from the center. If we assume the original crowd was placed randomly, then people at that distance should still be spread evenly. But if we instead assume that the crowd was arranged by first choosing a certain height above the stadium and then selecting positions at that height, the distribution along the given distance changes. This kind of problem appears in physics and engineering. In signal processing, for example, probabilities are often conditioned on specific frequencies or amplitudes. If the wrong conditioning method is used, it can lead to incorrect predictions. In quantum mechanics, the same issue arises when determining the likelihood of finding a particle in a certain state. How the measurement is taken affects the result. The lesson from Borel's paradox is that conditional probability is not always straightforward. When working with continuous distributions, the method used to impose conditions can change the outcome. This is different from finite probability, where conditional probabilities are fixed once given conditions are set. Another way to understand the paradox is through Bayesian statistics. In Bayesian probability, updating beliefs based on new information is fundamental. But if different ways of conditioning lead to different results, then the method of updating matters. This has implications for machine learning, artificial intelligence, and decision theory, where probabilities are constantly updated based on new data. To resolve the paradox, mathematicians use measure theory, which provides a rigorous way to define probabilities in continuous spaces. Measure theory ensures that probability distributions remain consistent regardless of how conditioning is done. However, in practical applications, people often work with approximations rather than exact measures. This means that awareness of paradoxes like Borel's is crucial to avoid errors in modeling. Ultimately, Borel's paradox is a reminder that probability theory is more subtle than it appears. It shows that intuition can fail when dealing with continuous distributions. It also highlights the importance of defining probability distributions carefully, especially when conditioning on specific events. In daily life, probability seems simple, like flipping a coin or rolling a die. But in deeper mathematical contexts, even basic ideas like conditional probability can lead to unexpected results. The paradox is not just a curiosity. It has real implications for statistics, physics, and data science. Understanding it helps avoid mistakes when interpreting probabilities in complex systems. It teaches that in probability theory, even small assumptions can lead to different conclusions. This makes it one of the many fascinating puzzles that arise when dealing with infinite sets and continuous spaces. The St. Petersburg Paradox is a thought experiment in probability that challenges how people evaluate risk and reward. It describes a gambling game with a seemingly infinite expected payout, yet most people would not be willing to pay much to play. This contradiction raises questions about how people perceive value and why they often make choices that do not align with mathematical expectations. The game is structured around flipping a fair coin. The rules are simple. A player flips the coin repeatedly until it lands on tails. The number of times the coin lands on heads before tails determines the payout. If the first flip lands on tails, the player wins $1. If the first flip is heads and the second flip is tails, the player wins $2. If the first two flips are heads and the third flip is tails, the player wins $4. The pattern continues, with the prize doubling for every additional heads that appears before the first tails. To calculate the expected value of this game, we look at each possible outcome and its probability. The chance of getting tails immediately is 1 out of 2, so the expected value for that outcome is half of $1. The chance of flipping heads first and then tails is 1 out of 4, making the expected value half of $2. The chance of getting 2 heads before tails is 1 out of 8, giving the same expected value. Since this pattern continues forever, adding up all these values leads to an infinite total. That means, according to probability theory, a rational person should be willing to pay any amount to play this game because the expected payout has no limit. However, in practice, people are not willing to pay large sums to enter. Most people might only offer a few dollars, even though the game supposedly offers unlimited potential winnings. This creates the paradox. If the expected return is infinite, why do people reject the game? This problem was first described in the 18th century by the Swiss mathematician Daniel Bernoulli. He proposed that people do not think about money in purely numerical terms. Instead, they consider how useful or valuable each additional dollar is to them personally. This idea is called diminishing marginal utility. It means that the more money a person has, the less valuable each extra dollar becomes. A poor person gaining $10 might feel a big impact, while a millionaire barely notices. Applying this idea to the St. Petersburg game explains why people refuse to pay large amounts to play. While the expected winnings are infinite on paper, the vast majority of payouts are small. Very large prizes are possible, but extremely rare. Since people value money differently depending on their situation, they are not motivated by mathematical averages alone. They care about how the money affects their lives in a practical way. Another reason people hesitate to play this game is psychological. Human beings tend to fear losses more than they seek gains. This idea is called loss aversion. If someone pays $50 to enter the game but wins only $1, they feel like they have wasted their money. Even if they understand that in the long run they would eventually win big, the emotional impact of losing makes them cautious. People are wired to avoid uncertain situations where a bad outcome, even if unlikely, feels too painful. This same tendency appears in real-world gambling. Casinos make money by offering games with a negative expected value, meaning the house always has an edge. Even though players mathematically lose over time, they keep playing because of the excitement and the possibility of winning big. The St. Petersburg game, however, lacks the small, frequent rewards that keep gamblers engaged. Most of the time, players win only a small amount, which makes the game feel unfair, even though the math says otherwise. A real-world example of similar decision-making happens in insurance. Many people buy insurance policies even when the expected financial return is negative. The probability of their house burning down, for instance, is very low, but they still pay for insurance to avoid disaster. They prefer certainty over risk, even if it means spending more than they are statistically likely to get back. This is similar to why they reject the St. Petersburg game. They prefer security and predictability over theoretical long-term gains. Economists and mathematicians have suggested ways to modify the game to make it more realistic. One idea is to set a maximum payout. In real life, no casino or individual has unlimited money. If the biggest possible prize is capped at a certain amount, the expected value of the game becomes finite. Another way to change the game is to slow the rate at which winnings increase, so they do not double every time. These adjustments make the game more practical and help explain why people would hesitate to play in its original form. A modern perspective on the paradox comes from behavioral economics. Studies show that people do not treat probabilities in a logical way. When dealing with very low chances, people often ignore them completely. For example, some people are afraid of flying even though air travel is much safer than driving. They focus on the worst possible outcome rather than its actual likelihood. The same reasoning applies to the St. Petersburg game. Players focus on the most common results, which are small payouts, and dismiss the rare but massive wins. The paradox also connects to stock market behavior. Investors prefer consistent, steady returns over risky but high-reward investments. A company that grows at a predictable rate is often seen as a better investment than one with higher returns but extreme volatility. The same principles apply to the game. Even though the possible winnings are enormous, most people prefer a more stable, less risky option. Lotteries provide another example of how people approach probability in a way that contradicts pure math. Many lotteries have massive jackpots but incredibly low chances of winning. Despite the poor odds, people buy tickets. In contrast, the St. Petersburg game offers an infinite expected value, yet few would pay much to enter. The key difference is how the potential rewards are framed. Lotteries highlight their biggest prizes, making them feel more attainable, even though they are just as unlikely as the large payouts in the St. Petersburg game. The paradox also applies to everyday decisions about risk and reward. Consider a person choosing between two job offers. One job pays a fixed salary, while the other offers lower pay but a chance at large bonuses. Even if the second job has a higher expected income, many people choose the first job because it feels safer. They prioritize certainty over potential long-term gains, just as they do when they reject the St. Petersburg game. Ultimately, the paradox highlights the difference between mathematical expectation and human behavior. In theory, people should make decisions based on expected value alone. In reality, they consider risk, emotions, and personal circumstances. The St. Petersburg game is an interesting example of how math can predict one thing, while real people behave in a completely different way. It shows that probability alone does not determine choices. The way people perceive risk and reward is just as important. 3 prisoners sit in their cells, waiting to learn their fate. They know that the warden will release one of them in the morning. The other 2 will remain in prison. The warden already knows which prisoner will go free, but the prisoners do not. Each of them believes they have a 1 in 3 chance of release. Before dawn, one prisoner decides to ask the warden for information. He reasons that if the warden names another prisoner who will stay, that should change the odds in his favor. The prisoner calls the warden over and makes a request. He does not ask directly about himself. Instead, he asks the warden to name one of the other 2 prisoners who will not be released. The warden considers this for a moment. He must always tell the truth, and he cannot name the prisoner who will be freed. If the warden already knows which prisoner will go free, he can always find at least one name to give. He points to one of the other 2 prisoners and says, "This prisoner will stay." Now the first prisoner feels more hopeful. He started with a 1 in 3 chance of going free. But now he knows one of the other 2 prisoners will not go free. That means there are only 2 prisoners left in the running, himself and the other prisoner who was not named. Since there are only 2 choices, he thinks the odds must now be even. His chance must have gone up to 1 in 2, or 50%. That logic feels correct at first. After all, 1 prisoner has been eliminated from the competition. But probability does not work that way. The key is understanding that the warden's choice was not random. He was forced to name a prisoner who was staying. The information the warden gave does not change the odds for the remaining 2 prisoners the way it seems. The original odds still hold. The prisoner who made the request still has only a 1 in 3 chance of release. The other prisoner, the one who was neither named nor asked, now has a 2 in 3 chance of going free. To see why this is true, consider what happens if the prisoner who made the request was already doomed. If he was never going to be released, then the warden had to name someone else. In 2 out of 3 cases, the warden had a choice of which prisoner to name. But in those cases, the prisoner who asked was never going free anyway. That means the remaining prisoner, the one who was never named, was the likely winner all along. It helps to compare this to a similar paradox, the Monty problem. In that case, a contestant picks a door, hoping to win a car. The host, who knows what is behind each door, opens another door to reveal a goat. The contestant then gets a choice: stick with the original door or switch. The best move is to switch because the host's choice is not random. The same logic applies to the 3 prisoners problem. The warden's statement does not randomly eliminate a prisoner from the competition. Instead, it reveals information in a way that changes the probabilities. A different way to see the answer is to play out all possible outcomes. Imagine the warden already knows the prisoner who will go free. The three prisoners do not. If the warden has chosen prisoner A to be released, then when prisoner B asks, the warden must name prisoner C. If the warden has chosen prisoner B, then when prisoner C asks, the warden must name prisoner A. If the warden has chosen prisoner C, then when prisoner A asks, the warden must name prisoner B. Now look at what happens when the prisoner who made the request considers switching places with the unnamed prisoner. If he was going to be released, switching is a bad idea. But if he was staying, switching is a good move. Since 2 out of 3 times the first prisoner was staying, switching to the unnamed prisoner wins in those 2 out of 3 cases. The unnamed prisoner had the better chance all along. This kind of probability puzzle confuses people because it seems like information should change the odds in a way that feels fair. Most people believe that if there are 2 choices left, each should be equally likely. But probability depends on how information is revealed, not just on how many options remain. The mistake comes from treating the warden's choice as if it were made randomly. But it was not. The warden's choice depended on knowing the outcome in advance. Many probability puzzles work in a similar way. One classic example involves drawing cards from a deck. Suppose you draw a card and do not look at it. You are told that it is either a king or a queen. Now someone looks at the card and tells you it is not the Queen of Hearts. That sounds like random information, but it is not. The person giving the information already knows the card. They are picking a way to describe it based on that knowledge. That changes the probabilities. A similar situation appears in real life with medical tests. If a doctor tells a patient they tested positive for a disease, the patient might think they have a high chance of having it. But the real chance depends on how common the disease is in the first place and how the test works. If a disease is rare, even a good test might give more false positives than real ones. This is an example of conditional probability, where new information must be analyzed based on the context in which it was given. Understanding conditional probability is important in many fields. In law, prosecutors use probability to argue guilt. But if evidence is selected in a way that is not random, the true probability might be different than it seems. In finance, stock market trends seem to follow patterns, but if analysts only look at successful examples, they might draw incorrect conclusions. In medicine, treatment success rates depend on sample sizes and selection methods. The 3 prisoners problem shows that people's instincts about probability are often wrong. Even when a situation feels simple, the way information is given changes everything. The warden does not eliminate a prisoner at random. He picks one based on prior knowledge. That is what makes the problem tricky. The prisoner who asked for information thought his odds improved, but they did not. The real winner was the prisoner who was never mentioned. Many people struggle with probability problems like this because they rely on intuition. But intuition is not always reliable when dealing with conditional probability. The best way to understand these problems is to break them down step by step. Looking at all possible outcomes makes it clear what is really happening. The 3 prisoners problem is not just a trick puzzle. It is a lesson in how probability works in real life. It teaches that information is only useful if we understand how it was selected. It reminds us to be careful when updating our beliefs based on new evidence. Even when something seems fair or logical, deeper analysis can reveal a different truth. The Banach-Tarski Paradox is one of the most surprising results in mathematics. It states that it is possible to take a solid ball, split it into a finite number of pieces, and then reassemble those pieces into 2 identical copies of the original ball. At first glance, this seems impossible. It suggests that something is being created from nothing, breaking the rules of common sense. But the paradox does not violate the laws of physics. Instead, it reveals the strange and counterintuitive nature of infinity. To understand why this paradox exists, it helps to start with the idea of dividing an object into parts. In everyday life, when something is split, the total amount of material stays the same. If a loaf of bread is cut into slices, the slices still add up to the whole loaf. Nothing is gained or lost. But in the Banach-Tarski Paradox, the pieces behave differently. They are not normal, solid pieces like slices of bread. Instead, they are infinitely complex sets of points that do not follow the usual rules of geometry. The paradox relies on a concept called non-measurable sets. In simple terms, a non-measurable set is a collection of points that does not have a well-defined volume. In regular mathematics, every shape has a size, whether it is a cube, a sphere, or a flat surface. Even a tiny dot has a measurable size of 0. But non-measurable sets are different. They exist in a way that prevents them from being assigned a clear volume. Because of this, it is possible to rearrange them in ways that seem impossible. To see how something like this might work, imagine a perfect sphere floating in space. If it could be cut into separate pieces with complete precision without losing a single point, then each piece could be moved and rotated in a special way. The rearrangement follows strict mathematical rules, ensuring that no points overlap or disappear. The result is two spheres that are each exactly the same as the original one. The key to the paradox is the nature of the pieces. In ordinary cutting, each piece has a clear boundary and a definite size. But in this process, the pieces are made up of infinitely scattered points, arranged in a highly complex pattern. Because of this, they do not behave like normal solid objects. They can be moved in ways that seem to defy logic, allowing for the creation of two full-size spheres from just one. The paradox depends on a mathematical concept called the axiom of choice. This axiom allows for the selection of points from an infinite set in a way that cannot be explicitly described. In practical terms, it means that the pieces used in the Banach-Tarski Paradox are not something that can be cut with a real knife or even visualized in a meaningful way. They exist only in the realm of pure mathematics, where sets can be constructed in ways that are impossible in physical reality. Despite its strange implications, the paradox does not violate the conservation of matter or energy. It cannot be used to duplicate objects in real life, and it does not suggest that new matter can appear out of nowhere. The process relies on ideal mathematical conditions that do not exist in the physical world. Atoms and molecules are not infinitely divisible, and real objects cannot be cut with infinite precision. The paradox exists as a statement about mathematical space, not about material objects. One way to think about this paradox is to compare it to an optical illusion. Just as certain drawings can trick the eye into seeing something that is not really there, the Banach-Tarski Paradox tricks intuition by relying on concepts that do not follow everyday rules. It is a reminder that mathematical truth can be very different from common sense. Infinity behaves in ways that often feel unnatural, and this paradox is one of the clearest examples of that. A similar concept appears in number theory with the idea of rearranging infinite series. Some infinite sums change their value depending on how their terms are arranged. For example, the alternating series 1 minus 1 plus 1 minus 1 plus 1 does not settle on a single sum. If grouped in one way, it appears to sum to 0. If grouped differently, it seems to sum to 1. This shows that infinity does not always follow the rules of finite arithmetic. The Banach-Tarski Paradox is another case where infinity allows for results that would be impossible in a finite setting. The paradox has also led to interesting discussions about the nature of space itself. If space were made up of discrete, indivisible units, then the Banach-Tarski construction would not work. This suggests that space might have a deeper mathematical structure than it appears. Some physicists have explored whether similar ideas could apply to the fabric of reality, but so far, there is no evidence that physical space behaves this way. Many people first encounter this paradox and react with disbelief. It seems to suggest a way to create wealth or energy from nothing. But the deeper one looks, the clearer it becomes that the paradox exists purely in the abstract world of mathematics. It does not provide a loophole for duplicating gold or generating infinite energy. Instead, it shows that the rules of infinite sets lead to surprising conclusions that challenge intuition. A useful way to test understanding of this paradox is to think about how it compares to other counterintuitive mathematical results. For example, the Hilbert's hotel paradox describes an imaginary hotel with an infinite number of rooms, where new guests can always be accommodated, even if every room is full. This also seems impossible at first, but it follows from the nature of infinite sets. The Banach-Tarski Paradox operates on similar principles, showing that infinite mathematics does not always match finite expectations. The paradox is also related to the concept of group theory, a branch of mathematics that studies symmetrical transformations. The way the pieces are rearranged in the Banach-Tarski process follows the rules of a special group of rotations and movements in three-dimensional space. This group, known as the free group, has properties that allow for non-measurable sets to exist. This connection to symmetry and transformation is one of the deeper insights behind the paradox. While the paradox itself is purely mathematical, it has inspired creative thought in other areas. Philosophers have used it to discuss the nature of identity and duplication. If a person were somehow subject to a process like the Banach-Tarski transformation, would the two resulting people both be the original? Would they have the same consciousness? These are thought experiments rather than practical questions, but they highlight how mathematical ideas can influence broader discussions about reality. The Banach-Tarski Paradox remains one of the most famous results in set theory and mathematical logic. It is an example of how formal mathematical reasoning can lead to conclusions that seem impossible. It does not have direct applications in physics or engineering, but it plays a role in understanding the structure of mathematical space. More than anything, it serves as a reminder that intuition is not always a reliable guide in the world of infinity. Gabriel's horn is a mathematical shape that leads to a surprising paradox. It has a finite volume, but an infinite surface area. At first, this seems impossible. If a shape can hold a limited amount of material, then it should not require an unlimited amount of paint to cover it. Yet, when we look at the mathematics behind it, this result turns out to be true. The shape is created by taking a simple mathematical curve and rotating it around an axis. The curve follows a rule where, as you move farther along the positive direction of the horizontal axis, the height of the curve keeps getting smaller, but it never actually reaches zero. When this curve is spun around the horizontal axis, it forms a three-dimensional shape that looks like a trumpet or a horn that stretches infinitely in one direction. The paradox comes from how the volume and surface area behave when we try to measure them. To understand why the volume is finite, we need to think about how much space this shape holds. When we calculate the volume, we find that it adds up to a specific, limited amount. This means that if we were to fill the horn with liquid or paint, we would need only a certain amount, no matter how far the horn stretches. Even though the shape extends forever, the total volume remains bounded. Now let's consider the surface area, which is the total amount of space on the outside of the horn. When we calculate this, we find that the surface area keeps increasing without limit. No matter how much paint we have, it would never be enough to completely coat the inside and outside of the horn. This is where the paradox appears. The shape can be filled with a finite amount of material, but it cannot be fully covered, no matter how much paint is available. This result feels strange because it goes against our everyday experience. If we think about an ordinary object, like a cup or a bottle, the amount of material needed to fill it is usually related to the amount needed to coat its surface. But Gabriel's horn stretches infinitely, and that makes a big difference. The key to understanding the paradox is realizing that volume and surface area do not always behave the same way. A useful way to think about this is to imagine a road that gets narrower and narrower as it stretches into the distance. If we want to cover the entire road with material, we only need to fill in the width of the road for as long as it goes. If the road starts wide but quickly becomes very thin, the total amount of material needed can still be finite. But if we want to paint the surface of the road, we have to account for every part of it, even as it keeps stretching into the distance. Since the road never ends, the amount of paint needed keeps increasing forever. Another way to explain the paradox is through a real-world analogy. Suppose we want to make a model of Gabriel's horn using clay. We could take a finite amount of clay and shape it into the horn, filling it completely. But if we try to coat the entire surface with paint, we would never be able to finish, because the surface area keeps growing indefinitely. This highlights the difference between volume and surface area. This paradox also appears in physics and engineering. While no real object can be infinitely long, the concept of an infinitely stretching shape helps scientists understand how different materials interact with space. Engineers deal with shapes that have very large surface areas compared to their volumes, such as insulation materials and coatings. Understanding the relationship between volume and surface area helps in designing materials with special properties. The paradox also teaches us about infinity. In everyday life, infinity is an abstract idea. We do not encounter truly infinite things. But in mathematics, infinity is a well-defined concept, and Gabriel's horn is a good example of how infinity can lead to results that seem contradictory. The shape stretches forever, yet its volume remains limited. This idea appears in many areas of mathematics, especially in the study of infinite series and limits. Historically, paradoxes like this have challenged mathematicians' understanding of space and measurement. When calculus was developed, mathematicians had to rethink basic ideas about shapes and sizes. Gabriel's horn is one of many examples where careful reasoning leads to results that defy intuition. It serves as a reminder that what seems obvious is not always true in mathematics. People often ask whether Gabriel's horn can exist in real life. If we mean a perfect mathematical version of it, the answer is no, because no real object can extend infinitely. But if we mean a practical approximation, then yes, scientists and artists could create a model that demonstrates the paradox. They would have to stop at some finite length, but the key idea would still be there. Another common question is whether this paradox has practical uses. While it may not have a direct application, the concepts behind it are important. The idea that volume and surface area can behave differently is useful in many fields. For example, in chemistry, nanoparticles have a very large surface area compared to their volume, which makes them useful in reactions and medicine. Understanding how surface area grows in comparison to volume helps scientists design better materials. Gabriel's horn is also a good example of how mathematics reveals surprising truths. Many people assume that if something has infinite surface area, it must also have infinite volume, or if something has finite volume, it must also have finite surface area. This paradox shows that those assumptions are not always correct. Mathematics often challenges our intuition and forces us to think in new ways. The paradox remains a fascinating topic for students, mathematicians, and anyone interested in the strange and counterintuitive results of infinity. It serves as a reminder that math is not just about solving equations, but about exploring ideas that expand our understanding of the world. Hilbert's hotel paradox is a thought experiment that shows how infinity challenges intuition. It describes a hotel with an infinite number of rooms, all occupied. At first, this seems like a problem. If every room is full, then no new guests should be able to check in. But infinity does not work like a regular number. Even though the hotel is full, the manager can still find space for new guests. This paradox helps explain how infinite sets behave in ways that seem impossible. Imagine an ordinary hotel with 10 rooms. If all 10 rooms are occupied and a new guest arrives, there is no way to accommodate them without someone leaving. Now replace 10 with infinity. The hotel has an infinite number of rooms and every room is occupied. A new guest arrives, but instead of turning them away, the manager shifts every guest to the next room. The guest in room 1 moves to room 2, the guest in room 2 moves to room 3, and so on. Since the hotel has infinite rooms, no guest is left without a place. This shift leaves room 1 empty, and the new guest checks in. The hotel remains full, yet it has made space for another person. A bus arrives with an infinite number of new guests. If the hotel were finite, there would be no way to fit them in. But the manager uses the same idea as before. Every current guest moves to a new room, but this time they move to the room that is twice their current number. The guest in room 1 moves to room 2, the guest in room 2 moves to room 4, the guest in room 3 moves to room 6, and so on. Since doubling a number always results in an even number, all current guests now occupy only even-numbered rooms. That leaves all odd-numbered rooms empty. The new guests move into these odd-numbered rooms, filling the spaces without displacing anyone. The hotel was already full, yet it made room for an infinite number of new arrivals. The paradox goes further. Suppose an infinite number of buses arrive, each carrying an infinite number of passengers. The hotel is still able to accommodate them. The manager assigns each current guest to a room based on powers of prime numbers. The guest in room 1 moves to room 2, the guest in room 2 moves to room 3, the guest in room 3 moves to room 5, and so on. Each guest moves into the next prime-numbered room. The passengers from the first bus are assigned rooms based on powers of 3, the second bus uses powers of 5, and so on. Since prime powers are unique, each guest from each bus receives a different room, and the hotel remains full. Hilbert's hotel shows the strange properties of infinite sets. In a finite hotel, adding guests would be impossible once it is full. In an infinite hotel, moving guests around creates space, no matter how many new arrivals come. This idea connects to how mathematicians compare the sizes of different infinities. Some infinities are larger than others, even though both are endless. The set of whole numbers is infinite, but so is the set of even numbers. Even though the even numbers seem smaller, each whole number pairs with exactly one even number, showing they are the same size. The hotel's shifting process follows the same principle. The paradox helps explain why infinity does not follow the rules of finite numbers. In everyday life, if a container is full, it cannot hold more. If a store has 10 shelves and every shelf is stocked, there is no space for extra products. But with an infinite system, moving things around can create new possibilities. The hotel remains full at every stage, but always finds space for more. This concept has practical applications in mathematics and computer science. Infinite sets appear in logic, probability, and programming. In networking, data can be structured in ways that resemble Hilbert's hotel, ensuring efficient storage and organization even when dealing with vast amounts of information. Understanding infinity helps in developing algorithms that handle large-scale problems. Some people struggle to accept the paradox because it contradicts intuition. People expect full to mean no more room. They assume infinity behaves like a very large number instead of something entirely different. But Hilbert's hotel follows the rules of infinite sets, which do not work the same way as finite ones. The paradox demonstrates why thinking about infinity requires a shift in perspective. A common mistake is assuming that infinity plus 1 is greater than infinity. In standard arithmetic, adding to a number makes it larger. But in an infinite set, adding a finite amount does not change the total size. The hotel remains just as full after adding a guest as it was before. This result seems strange, but follows logically from how infinite sets behave. The paradox also connects to real-world problems in philosophy and physics. Some theories about the universe involve infinite space or time. If the universe is infinite, then Hilbert's hotel suggests that making room for new events does not require removing past ones. Some interpretations of quantum mechanics consider an infinite number of parallel realities, where shifting between possibilities resembles moving guests in an infinite hotel. The concept also applies to decision-making. Suppose a company schedules an infinite series of meetings, each lasting half as long as the previous one. Even though there are infinitely many meetings, they fit within a finite amount of time. This mirrors how the hotel remains full, yet accommodates more guests. Understanding infinity helps in fields like economics, where resources can be distributed in ways that maximize availability. Hilbert's hotel does not exist in real life, but its lessons shape how mathematicians think about infinity. It shows that infinite sets behave in ways that defy normal expectations. The hotel remains full, yet it always has space. The paradox reveals the power of mathematical reasoning to challenge intuition and expand understanding. The Hausdorff Paradox is a surprising result in mathematics that challenges intuition about size and division. It shows that under certain conditions, a solid object like a sphere can be broken into a few pieces and rearranged into something that looks much bigger. The paradox is similar to the Banach-Tarski Paradox, but it applies to a single sphere rather than using two separate objects. This idea comes from set theory and geometry, revealing strange properties of infinity and space. To understand the Hausdorff Paradox, it helps to think about what it means to split something into parts. In everyday life, when a cake is cut into slices, the total amount of cake stays the same. No matter how the pieces are rearranged, they still form the original cake. The same is true for physical objects. If a ball is cut into two halves and reassembled in a different way, it does not magically become larger. But in the world of mathematics, certain ways of dividing space do not follow these rules. The paradox starts with an ordinary sphere in three-dimensional space. The goal is to break this sphere into a small number of disjoint pieces, meaning each piece contains points that do not overlap with points from another piece. After separating the sphere, the pieces can be rearranged using rigid motions, rotations, and translations, so that they form a larger version of the same sphere. Unlike cutting a cake, these pieces are not simple shapes with clear edges. Instead, they are strange sets of points that do not behave like normal objects. To see why this works, it is necessary to get a concept called non-measurable sets. Normally, when measuring objects, there is a clear way to assign a size to each piece. A ruler can measure length, a scale can measure weight, and a measuring cup can determine volume. But in set theory, it is possible to construct sets that do not have a well-defined measure. These sets exist in mathematics, but do not correspond to anything physical in the real world. They are the key to the paradox. The Hausdorff Paradox relies on the fact that certain rotations in three-dimensional space behave unpredictably when applied infinitely many times. A useful example comes from rotating a sphere. Imagine placing a dot on the surface of a ball and then rotating the ball slightly. If this rotation is repeated many times, the dot moves around in a way that seems random. However, for some carefully chosen rotations, the dot will never return to its original position. Instead, it will cover the sphere in a complicated way, spreading its movement over the entire surface without forming a regular pattern. This behavior allows the sphere to be split into distinct parts in a way that defies normal intuition. The key is to use a set of rotations that shuffle points around the sphere, so that each point ends up in a different, non-overlapping group. Because these groups do not have well-defined sizes, they can be rearranged to cover more space than they originally occupied. This is how a single sphere can appear to be duplicated without adding any new material. A similar effect happens in the Banach-Tarski Paradox, which shows that a sphere can be divided and rearranged into two spheres of the same size as the original. The Hausdorff Paradox differs because it works with only one sphere without requiring duplication. The outcome still seems impossible, but the underlying idea remains the same. Certain ways of dividing space do not behave in the way people expect. This paradox does not work in the physical world because real objects are made of atoms, which cannot be divided infinitely. The process depends on splitting a sphere into infinitely complicated pieces, something that is only possible in an abstract mathematical setting. In reality, a ball made of solid material would resist being divided this way, because matter is not infinitely divisible. But in pure mathematics, where space is treated as an infinite collection of points, there is nothing stopping this kind of division. One way to think about the paradox is through the idea of symmetry. Many mathematical structures have symmetries, which means they look the same after being rotated or reflected. A circle, for example, looks the same after being rotated by any angle. A sphere has even more symmetries, since it can be rotated in any direction and still look unchanged. These symmetries allow for the strange kind of division used in the Hausdorff Paradox. Another useful comparison comes from the concept of tiling. In ordinary tiling, a floor can be covered with square tiles without gaps or overlaps. But some tilings exist where the pattern never repeats. The most famous example is Penrose tiling, which covers a surface with shapes that follow certain rules but never form a repeating pattern. The pieces in the Hausdorff Paradox behave in a similar way. They are not shaped like normal geometric objects, and they follow rules that prevent them from being measured in the usual sense. The paradox also raises questions about how infinity works. In many mathematical problems, infinity leads to results that seem strange. For example, in the Hilbert's hotel paradox, an infinite hotel can always fit more guests even when it is full, simply by shifting existing guests to different rooms. The Hausdorff Paradox shows another strange consequence of infinity. It demonstrates that in some cases, an object can be broken apart and rearranged into something that looks bigger, without actually adding any new points. This paradox also has connections to group theory, which studies mathematical objects that have symmetry. The particular group involved in the Hausdorff Paradox is the group of rotations in three-dimensional space. These rotations follow specific mathematical rules, but they also allow for the unexpected behavior that makes the paradox possible. By carefully choosing certain rotations, it is possible to break a sphere into pieces that can be moved around in ways that defy normal expectations. Although the paradox does not work in physical space, it has real-world applications. Some areas of computer science use similar ideas to solve problems in graphics and data structures. Certain encryption methods rely on complex group structures, similar to those used in the Hausdorff Paradox. Understanding how space can be divided and rearranged also has uses in theoretical physics, where space and time behave differently at very small or very large scales. The Hausdorff Paradox is an example of how mathematics can challenge intuition. It shows that in some cases, the normal rules of size and measurement do not apply. The paradox depends on the structure of space and the way points are arranged. It does not allow for an actual increase in material, but it demonstrates that mathematical objects can behave in surprising ways when infinity is involved. The paradox teaches valuable lessons about the nature of measurement, symmetry, and the strange consequences of infinity. The Klein bottle is a strange mathematical object that challenges the way people think about surfaces and dimensions. It looks like a bottle, but it does not have an inside or an outside in the usual sense. If someone tried to pour liquid into it, the liquid would not stay inside because the bottle does not enclose a space. This is because the Klein bottle is a non-orientable surface, meaning it has no distinct left or right sides. To understand what makes the Klein bottle so unusual, it helps to start with something simpler: a Mobius strip. A Mobius strip is a loop of paper with a half twist before the ends are joined together. If someone traces a line along the surface, they will eventually return to where they started, but they will have covered both sides of the paper without crossing an edge. In a normal loop of paper, there are two separate sides, but in a Mobius strip, there is only one continuous surface. The Klein bottle takes this idea further. A Klein bottle is like a Mobius strip, but in a higher dimension. In three-dimensional space, creating a true Klein bottle is impossible without self-intersection. A common model of a Klein bottle looks like a bottle with a neck that loops around and passes through the side of the bottle, connecting back to the bottom. But in four-dimensional space, a Klein bottle does not have to intersect itself. It exists as a smooth, continuous surface with no true boundary. The idea of a surface without an inside or an outside is hard to picture. Most objects in daily life have an interior and an exterior. A sphere, for example, has an outer surface, and if it is hollow, it has an inner surface as well. But the Klein bottle is different. If a small insect walked along its surface, it could move from what seems like the inside to the outside without crossing a boundary. There is no way to separate one side from the other. This creates a paradox because it challenges the normal understanding of space. If something has an inside, there must be an outside. If someone draws a boundary around an area, there should be a clear distinction between what is enclosed and what is not. The Klein bottle defies this expectation. It is a single surface, but it cannot be divided into two separate regions. One way to make sense of this is to think about dimensions. In 2 dimensions, a person can move left, right, forward, or backward, but they cannot move up or down. If a 2-dimensional creature lived on a piece of paper, it would not be able to see above or below the paper. If the paper were folded into a Mobius strip, the creature would experience a strange effect. It could walk in one direction and eventually return to its starting point, but flipped. The Klein bottle does something similar in 3 dimensions. It connects back to itself in a way that creates a single continuous surface. Mathematicians describe the Klein bottle using equations and topology. In topology, objects can be stretched or bent without changing their fundamental properties. A coffee cup and a donut, for example, are considered the same in topology because one can be reshaped into the other without cutting or adding holes. The Klein bottle belongs to a class of objects that do not have clear boundaries. It is related to the Mobius strip and the projective plane, both of which have unique properties. Although a true Klein bottle cannot exist in three-dimensional space without intersecting itself, people create physical models to help visualize it. These models often use glass or plastic and include a tube that appears to pass through the bottle's surface. But this is just a representation. In four-dimensional space, no such intersection would be necessary. The Klein bottle would smoothly loop back onto itself without breaking any rules of geometry. This raises an interesting question about dimensions. People are used to thinking in 3 dimensions, but higher dimensions exist in mathematics and physics. Many theories in physics, including string theory, suggest that more dimensions exist beyond what can be seen. The Klein bottle provides a way to imagine how objects might behave in spaces beyond ordinary experience. The paradox of the Klein bottle extends beyond mathematics. It has implications in philosophy and logic as well. If something does not have an inside or an outside, what does it mean for something to be contained? If a boundary does not separate one area from another, what does it mean to be inside a space? These questions show how mathematics can challenge basic assumptions about reality. People also see similar ideas in art and design. Some artists use Mobius strips and Klein bottle shapes in sculptures and paintings to explore ideas of infinity and paradox. Architecture sometimes borrows from these concepts to create buildings with unexpected layouts, where spaces flow into each other in unusual ways. In practical applications, the Klein bottle does not have many direct uses, but it appears in computer science and physics. In data structures, certain algorithms use principles related to topology to manage complex networks. In physics, some theories about space-time and the universe involve structures that resemble a Klein bottle in certain ways. The Klein bottle is also a favorite subject in mathematical puzzles and recreational mathematics. Many people enjoy trying to build models or find new ways to describe its properties. It is a reminder that not everything in mathematics follows common sense. Some objects defy expectations and force new ways of thinking. For those who want to explore further, making a Klein bottle model at home is an interesting challenge. While a true Klein bottle cannot exist in three-dimensional space, a close approximation can be made with flexible tubing. By connecting a tube in a way that loops back through itself, a model can be created that gives a sense of how the shape works. Some people also use computer simulations to visualize how a true Klein bottle would appear in four-dimensional space. The Klein bottle remains one of the most fascinating objects in mathematics because it challenges the way people think about space and surfaces. It does not fit into the usual categories of shapes and forces a reconsideration of what it means for something to be inside or outside. It is a simple object in one sense, just a continuous surface, but in another sense, it is deeply puzzling. It serves as a reminder that mathematics is not just about numbers, but also about exploring ideas that go beyond what can be seen or touched. It is a window into a world where intuition does not always match reality, and that is what makes it so compelling. The four-color theorem is a mathematical rule about maps. It says that no matter how complex a map is, you never need more than 4 colors to make sure no 2 neighboring regions share the same color. A neighboring region means 2 regions that share a border, not just a point. This rule applies to maps drawn on a flat surface, like a piece of paper, or on a sphere, like a globe. The idea behind the theorem is simple, but proving it took over a century. The problem started in the 1850s, when Francis Guthrie, a mathematician, noticed something interesting. He was coloring a map of England and realized that 4 colors were always enough. He asked his professor, Augustus de Morgan, if that was always true. De Morgan did not know, and neither did anyone else at the time. The question turned into a major mathematical challenge. For years, many mathematicians tried to prove the theorem. Some thought they had succeeded, but their proofs had mistakes. The problem seemed simple, but solving it was much harder than expected. In 1879, Alfred Kempe came up with a proof, and most people believed it. However, in 1890, Percy Heawood found an error. That meant the problem was still unsolved. The search for a proof continued. Mathematicians checked different kinds of maps in special cases. They used logical rules to try to show that 4 colors were enough for all possible maps. They made progress, but a complete proof remained out of reach. The breakthrough finally came in 1976, thanks to Kenneth Appel and Wolfgang Haken. They used computers to help check many cases, something no human could do by hand in a reasonable amount of time. Their proof was the first to rely on computer calculations. At the time, some mathematicians did not like this approach because they could not verify every step by hand. But over time, the proof gained acceptance, and no one has found any mistakes. To understand why the theorem works, imagine drawing a map. Each region needs a color different from its neighbors. If there were only 2 regions, 2 colors would be enough. If there were 3 regions, 3 colors might be needed. But when maps get more complex, the number of colors required does not keep increasing. No matter how many regions there are, 4 colors are always enough. Think of a simple example. Suppose you draw a square and divide it into 4 sections. You want to color the sections so that no 2 touching sections have the same color. You start with one section and color it red. The section next to it must be a different color, so you choose blue. The third section touches both red and blue, so you pick green. The last section touches only 2 others, so you can use red again. That works, and no section breaks the rule. Now imagine a more complicated map. It has many regions, different shapes, and no clear pattern. You might think it needs 5 or more colors, but that is never the case. No matter how you draw the borders, you can always find a way to use just 4 colors. The proof is difficult, but the result is simple. The theorem does not apply to maps on surfaces other than a plane or sphere. If you draw a map on a torus, which is the shape of a donut, 4 colors are not always enough. Some maps on a torus need 7 colors. The reason has to do with how the surface bends and connects. But for flat maps and globes, 4 colors are always sufficient. Real-world maps follow this rule, even if people do not realize it. If you look at a political map of a country, you will see different colors for different states or regions. Cartographers, the people who make maps, often use 4 colors or fewer. They do not need to know the mathematical proof to use the rule. It simply works. The 4-color theorem is useful beyond maps. It helps in scheduling problems where different tasks need different time slots. If 2 tasks cannot happen at the same time, they are like neighboring regions on a map. The goal is to schedule everything with the fewest time slots, just like coloring a map with the fewest colors. The theorem also has applications in computer science, network design, and even puzzles like Sudoku. Understanding why 4 colors are enough can be tricky, but thinking through simple cases helps. If a map needed 5 colors, there would have to be a region that touches 4 other regions, each a different color. That can happen, but it never forces a 5th color. There is always a way to arrange the colors so that 4 are enough. Some people wonder why a proof was necessary. If no one ever found a map needing 5 colors, why not just accept that 4 was enough? The answer is that mathematics does not work that way. A pattern may hold in many cases, but still fail in one unusual case. A proof guarantees that no exception exists. Mathematicians still study the 4-color theorem today. They look for different ways to prove it, some that do not require computers. They also explore related problems, like how many colors are needed on different surfaces. The problem led to new ideas in graph theory, which studies connections between points. It also showed that computers could be valuable tools in proving theorems. The theorem is a reminder that simple questions can have deep answers. It started with someone coloring a map and led to over a century of research. Even though the problem is solved, it still fascinates people. It shows how mathematics can turn everyday observations into major discoveries. It also proves that some truths, even when they seem obvious, need careful proof. When people first hear about the theorem, they often try to find an exception. They might draw complicated maps and experiment with colors, but every time they see that 4 colors are enough. This is part of what makes the theorem interesting. It is easy to test and see in action, even without understanding the proof. The 4-color theorem is a milestone in mathematics. It took intuition, persistence, and new technology to solve. It changed the way people think about maps and graphs. It also introduced new ways of proving things, showing that computers could help answer questions humans could not solve alone. Even though the result is simple, the journey to proving it was one of the most challenging in mathematical history. The Menger sponge is a mathematical shape that defies normal intuition. It is a fractal, which means it has a repeating pattern at every level of magnification. The paradox of the Menger sponge comes from two facts that seem impossible together. As you keep cutting away parts of the shape, its surface area keeps increasing without limit. At the same time, its volume shrinks towards zero. This creates a shape with infinite surface area but no volume, which challenges basic ideas about space and size. To understand the Menger sponge, start with a simple cube. Imagine a solid block. Now divide this cube into 27 smaller cubes, like a Rubik's cube. Remove the middle cube from each face and the center cube inside. That leaves 20 cubes still in place. This is the first step in creating the sponge. Now take each of the 20 remaining cubes and repeat the process. Cut them into 27 smaller cubes and remove the middle sections again. You now have a more complex shape with even more holes. Repeat this process indefinitely. Each time, more of the cube is removed, creating a shape that gets more intricate as it develops. At first, it seems like the shape is just becoming more and more porous. But something surprising happens. Every step removes more volume, but the total surface area keeps growing. If you continue this process infinitely, the volume approaches zero. There is almost nothing left of the original cube. However, the surface area keeps increasing, expanding without limit. This is the paradox, an object with no volume but an infinitely large surface. To make sense of this, think about painting a shape. A regular cube has a fixed surface area that you could cover with a set amount of paint. If you start turning that cube into a Menger sponge, the amount of paint you would need to cover its surface starts growing. Each new stage adds more faces, edges, and surfaces, making the total area larger. If you continue forever, no amount of paint will ever be enough to cover it completely. But at the same time, the cube itself has almost disappeared. There is no solid material left, just an intricate web of infinitely thin surfaces. This happens because of the way the shape evolves. In each step, you remove material from inside the cube, which reduces its volume. But each removal exposes new surfaces. Since this process never stops, the surface continues growing while the volume continues shrinking. The Menger sponge is an example of a fractal. A fractal is a shape that looks similar at every level of zoom. No matter how close you look, the pattern remains the same. The Menger sponge follows this rule. If you zoom in on one part, you see tiny versions of the whole shape. This property is called self-similarity. Many natural patterns, like coastlines and snowflakes, show some level of self-similarity, but the Menger sponge is an extreme case. This fractal also challenges the idea of dimension. Normally, a cube is three-dimensional. It has width, height, and depth. A flat shape, like a square, is two-dimensional. A line is one-dimensional. The Menger sponge is somewhere in between. It is more than two-dimensional because it has depth, but it does not completely fill three-dimensional space. Its true dimension is a fraction, about 2.73. This is called its fractal dimension, a concept used in mathematics to describe shapes that do not fit neatly into whole-number dimensions. The paradox of infinite surface area and zero volume is not just a curiosity. It has practical implications in science and engineering. For example, the idea of increasing surface area while reducing volume is useful in designing materials with high efficiency. Sponges, filters, and catalysts benefit from having large surface areas. A Menger sponge-like structure could maximize interactions between surfaces while using very little material. Some biological structures work in a similar way. The human lungs, for example, have a branching structure that increases their surface area. This allows them to absorb more oxygen without taking up too much space. Some types of coral and fungi also grow in fractal-like patterns, maximizing exposure to their surroundings. The Menger sponge also appears in computing and technology. The way networks and circuits are designed often takes inspiration from fractals. A shape with infinite surface area can be useful for antennas, which need to capture signals from a wide range of directions. Some antennas are designed using fractal principles, improving their performance. One way to think about the paradox is to imagine filling a Menger sponge with liquid. A normal cube holds a fixed amount of liquid based on its volume. But a Menger sponge, after many steps of cutting, holds almost nothing. If you tried to pour water into it, most of the water would leak out. Yet, if you tried to coat it with a layer of paint, you would need an impossible amount because the surface never stops growing. Another way to visualize this is by thinking about a piece of paper. If you fold a sheet of paper in a complex way, you can increase its surface area. Imagine folding it endlessly, cutting tiny holes and stretching it. The surface keeps increasing, but the material itself does not expand. The Menger sponge takes this idea to the extreme, pushing it to infinity. Even though the Menger sponge exists mostly in theory, people have built physical models. Artists, engineers, and mathematicians have used materials like paper, foam, and plastic to create approximations. Of course, a real model cannot go on forever. It must stop at some level because of physical limits. But these models still capture the essence of the paradox, showing how a simple process can lead to surprising results. One interesting experiment involves building a Menger sponge out of business cards. By folding and connecting the cards in a certain way, people have constructed large-scale versions of the shape. This hands-on approach makes the concept easier to understand. Seeing the shape in real life helps people grasp how its surface grows while its volume shrinks. The paradox of the Menger sponge is a reminder that mathematics does not always match intuition. Most people expect that a shape with zero volume should not have any surface at all, but the rules of fractals show otherwise. It is one of many examples where math reveals something surprising about the nature of space and structure. Mathematical paradoxes like this have a way of changing how people think about shapes, space, and even reality. They challenge assumptions and force deeper understanding. The Menger sponge is not just a strange shape. It is a gateway to exploring the ideas of infinity, dimensions, and fractals. Whether in nature, technology, or pure mathematics, it offers insight into how complex patterns emerge from simple rules. Cauchy's functional equation is a simple rule that leads to unexpected and strange results. The rule states that if you take any two numbers, apply a function to each, and then add the results, you should get the same answer as if you first added the two numbers together and then applied the function. At first, this seems straightforward. The most natural function that follows this rule is one that multiplies every number by a constant. This is what most people would expect, and in many cases, it is the only solution. But in some mathematical settings, other solutions exist, and they behave in ways that do not match intuition. To see why this is strange, imagine a simple scenario. Suppose a worker gets paid based on the number of hours they work. If the pay is consistent, then working 3 hours today and 5 hours tomorrow should give the same total payment as working 8 hours all at once. This follows the structure of Cauchy's rule. Splitting work into parts does not change the overall pay. This kind of pattern appears in many areas, from measuring distances to counting objects to keeping track of time. In most normal cases, this rule leads to predictable behavior. But the equation does not say anything about how the function must behave between whole numbers, nor does it require the function to follow a smooth or logical pattern. It only says that if you take two numbers, apply the function separately to each, and then add the results, it must match the value of the function applied to the sum. If we assume the function behaves in a smooth and continuous way, then the only possibility is the expected one, where the function multiplies by a constant. But if we remove that assumption, strange things start to happen. The most unusual solutions to this problem do not behave in any smooth or predictable way. They can jump between values in ways that make no sense from a practical standpoint. These solutions are called pathological because they follow the rule, but do so in an irregular, non-intuitive way. They are not constructed using a simple formula. Instead, their existence relies on deep mathematical principles, particularly something called the axiom of choice. This principle allows numbers to be selected in a way that does not follow an obvious pattern. With this method, mathematicians have found functions that obey the equation but behave in ways that are impossible to describe with an ordinary formula. To understand why this is a problem, think about measuring distances. Suppose you are mapping a city and need to calculate the distance between different locations. Normally, if you measure the distance from one point to another and then add another segment, the total should match the direct measurement from start to finish. But if distances followed the logic of these strange functions, the results could be inconsistent. The measurements might still obey the rule that adding two separate distances gives the total, but the values themselves could seem random. This leads to a paradox. When people first see Cauchy's rule, they expect only one answer: the simple function that multiplies by a constant. This expectation comes from everyday experience, where things behave in predictable ways. But as soon as we remove assumptions like smoothness, new solutions appear. These solutions are not random, but they do not follow any pattern that can be written as a simple formula. This is surprising because most people assume that mathematical rules always lead to clear, logical answers. A practical way to think about this is through temperature measurements. Imagine a thermometer that follows the usual rule. If you check the temperature in the morning and again in the afternoon, the difference in readings should match the total change. But now, suppose the thermometer is built in a way that causes it to display unpredictable numbers while still obeying this rule. The individual temperature readings would make no sense, yet the rule itself would still hold. This is similar to how these strange functions behave. These functions do not appear in most real-world applications because they require an unusual mathematical structure. In practical settings, assumptions like continuity prevent them from existing. In physics, for example, equations that describe motion rely on smooth functions. If these strange, discontinuous functions existed in nature, they would lead to measurements that jump unpredictably. This is why they are mostly studied in pure mathematics rather than in applied fields. Even though they are impractical, these strange functions reveal something important about mathematical reasoning. They show that even simple rules can have unexpected solutions when constraints are removed. Many areas of mathematics rely on extra assumptions, such as smoothness or predictability, to prevent such solutions from appearing. But when those assumptions are dropped, counterintuitive results emerge. One way to see this in everyday life is in financial markets. Suppose someone tries to predict stock prices using a formula that assumes prices follow smooth patterns. If the market instead behaves unpredictably while still obeying basic rules of addition, the formula will fail. In this case, the stock prices resemble the strange functions that obey the equation but do not follow a clear pattern. The Cauchy functional equation connects to deeper questions about how functions behave. It links to ideas in set theory, measure theory, and mathematical logic. It also highlights the role of assumptions in math. Many results that seem obvious depend on hidden conditions. This paradox shows that when assumptions like continuity are removed, unexpected things can happen. Mathematics often reveals truths that are not immediately clear. The Cauchy equation appears simple, yet its unrestricted solutions challenge intuition. It serves as a reminder that mathematical reasoning depends not just on rules, but also on the assumptions behind them. Understanding this paradox helps clarify how mathematical structures work and why certain conditions are necessary for predictable results. The Divergence Paradox is the idea that some mathematical series seem like they should add up to a finite number, but actually grow without limit. This surprises many people because the terms in these series get smaller and smaller. It feels like they should settle at some final value. But in some cases, no matter how many terms you add, the total keeps increasing forever. The most famous example is the harmonic series. The harmonic series begins with 1 and then adds smaller and smaller fractions. It starts with 1, then adds 1/2, then 1/3, then 1/4, then 1/5, and so on. Each new term is smaller than the one before it, so it seems like the total should eventually stop growing, but it does not. The sum increases without bound, even though it does so very slowly. To see why this happens, imagine you start adding these numbers together. The first term is simply 1. Adding 1/2 brings the total to 1.5. Adding 1/3 increases the sum to a little more than 1 4/5. Then adding 1/4 raises it slightly above 2. As you keep adding more terms, the amount you add gets smaller and smaller, but the total keeps creeping up. It never settles at a final number. If you keep adding more terms, the sum will eventually exceed any number you choose. A way to understand this is to group the terms in a certain way. Consider these groups: the first number by itself, then the next number alone, then the next two numbers together, then the next four numbers together, and so on. Each time, the number of terms in a group increases. But even though there are more terms in each group, the total of each group remains at least 1/2. That means as you keep adding more groups, you keep adding at least 1/2 over and over again. Since there is no end to these groups, the total must continue growing forever. This result confuses many people at first. It seems like anything made of smaller and smaller parts should eventually stop growing. But the harmonic series proves that is not always true. It reminds us that intuition about numbers is not always reliable. Just because something shrinks does not mean it disappears. There are practical ways to see this idea in action. Imagine a stack of books where each book is half the thickness of the one below it. If you add just a few books, the stack remains short. But if you keep adding thinner and thinner books, the stack keeps growing. There is no limit to how tall it can get, even though each book adds very little height. The same thing happens with the harmonic series. This concept appears in physics and engineering. For example, electrical circuits sometimes use resistors arranged in a sequence. The total resistance is the sum of the individual resistances. If you keep adding resistors with smaller and smaller values, the total resistance might grow without limit. The same issue can happen in mechanical systems, where small effects build up over time. Another example appears in nature. Some populations of animals or bacteria grow in a way that looks like the harmonic series. Each new generation is slightly smaller than the last, but the total population keeps increasing. This can cause ecosystems to reach a breaking point when they seem like they should stabilize. The Divergence Paradox also has consequences in finance. Suppose you earn money from an investment, but the returns shrink each year. If those returns follow the harmonic series, your total earnings will still grow forever. Even though each year adds less than the previous one, the total amount never stops increasing. In mathematics, there are many series that look like the harmonic series but behave differently. If you change the fractions in a small way, the series might stop growing at some limit. For example, if you replace each fraction with the square of its value, the total sum will stay finite. The terms shrink fast enough that they do not allow the total to grow forever. This shows that small changes in a series can make a big difference. There are other famous divergent series. One example is the sum of all whole numbers, starting from 1 and continuing forever. This sum grows even faster than the harmonic series. Some people have claimed that this sum equals a strange value, but that result only makes sense in a special context. In the usual sense, the sum just keeps increasing. The idea of divergence appears in calculus, where it helps define certain types of integrals. Some functions seem to have a finite area under their curve, but actually stretch to infinity. This happens in problems involving physics, like calculating the energy of a system. If an equation leads to a divergent result, it often means something is missing from the model. Understanding divergence helps in real-world decision-making. In statistics, some averages depend on whether a series converges or diverges. If an average involves a divergent sum, the result is misleading. This affects economics, where some cost estimates depend on infinite sums. If those sums diverge, the costs might be much higher than expected. Divergence also affects computer science. Some algorithms use infinite series to estimate values. If a series diverges, the algorithm might never finish or produce incorrect results. Programmers must check whether their calculations involve divergence to avoid errors. This paradox reminds us to think carefully about infinite processes. It shows that just because something grows slowly does not mean it will stop. It also warns us not to trust intuition when dealing with infinity. Math often leads to results that seem surprising but are true. The harmonic series is one example, and its lessons appear in many fields. The Riemann rearrangement theorem shows that infinite sums, when arranged differently, can lead to completely different results. It applies to a specific type of infinite sum known as a conditionally convergent series. The surprising outcome is that by simply changing the order of terms, the total sum can become any number, even positive or negative infinity. This challenges the way we usually think about addition because, in everyday arithmetic, the order in which numbers are added does not change their total. However, when dealing with infinity, our usual rules no longer apply. To understand this better, imagine a well-known mathematical series where numbers are added together in a specific order. This series begins with 1, followed by subtracting half, then adding a third, then subtracting a fourth, and continuing in this pattern, alternating between addition and subtraction while the numbers get smaller and smaller. If we continue this process forever, the sum approaches a fixed value. This means that if we keep adding more terms, the total does not grow indefinitely, but instead settles toward a particular number. At first, this seems simple. However, what Riemann discovered was that if we take this same series and rearrange its terms, we can force the sum to approach any value we want. This is not just a trick, it is a fundamental property of conditionally convergent series. The reason this happens is that the positive numbers in the series are growing toward infinity on their own, while the negative numbers are also pulling the total downward toward negative infinity. When these two forces balance in a specific order, they settle toward a particular number. But if we change that order, we can shift this balance, making the total reach any desired outcome. To see how this works, consider trying to make the sum equal a large number, like 10. We can do this by starting with enough positive numbers to push the total just above 10. Then we add a negative number to bring it slightly below 10. We continue this pattern, adding more positive numbers to go back above 10, then another negative number to bring it just under 10 again. By carefully choosing how many positive and negative numbers to include at each step, we can force the sum to stay close to 10 indefinitely. This technique can be used to reach any number, proving that the sum is not fixed, but depends entirely on the order in which the numbers are added. This result is shocking because it contradicts what most people assume about arithmetic. If we add up a group of numbers, we expect the order to make no difference. If someone were counting coins, for example, it would not matter if they counted them in a different order. The total number of coins would remain the same. But with an infinite sum of certain numbers, this is no longer true. Changing the order changes the outcome. This happens because the series is conditionally convergent. This means that while the original order leads to a specific total, the sum of all the positive numbers alone would grow toward infinity, and the sum of all the negative numbers alone would also move toward negative infinity. The fact that the series settles to a specific number in one order is a delicate balance between these two opposing forces. When that order is disrupted, the balance shifts, leading to a different result. A helpful way to think about this is by imagining an account where money is constantly being deposited and withdrawn. If someone deposits $1, then withdraws a slightly smaller amount, then deposits again, and keeps repeating this process, the total balance will grow but slowly. If instead withdrawals were arranged differently, the balance might end up completely different, even though the same transactions occurred. The timing and sequence of additions and subtractions make a significant impact when dealing with infinite sums. This also reveals something strange about the nature of infinity. Most of the time, when people think about infinity, they imagine something very large, but this theorem shows that infinity does not behave in a predictable way. It is flexible and depends on how it is approached. When summing an infinite list of numbers, small changes in how those numbers are arranged can completely alter the final result. This means that infinity is not just big, it is unpredictable. This concept has important applications in different areas of mathematics and science. In physics, for example, infinite sums appear in theories of waves, quantum mechanics, and signal processing. The order in which calculations are performed can sometimes affect the interpretation of physical results. Mathematicians and scientists must carefully consider whether a series is absolutely convergent, meaning its total remains the same no matter the order, or conditionally convergent, meaning it can be manipulated to produce different outcomes. In practical applications like computer science, this issue appears in numerical calculations. Computers work with approximations of real numbers, and when adding many numbers together, the order of operations can lead to small rounding errors. In some cases, these small errors accumulate, leading to significant differences in results. Engineers designing algorithms for large computations must be aware of how numbers are summed to ensure accuracy. The Riemann rearrangement theorem is one of those discoveries that initially seem impossible. It goes against what most people assume about addition and forces us to rethink basic principles when dealing with infinity. It shows that infinite processes can behave in unexpected ways, where order becomes just as important as the numbers themselves. A useful analogy is stacking grains of sand. If a person carefully places each grain one by one, they might form a smooth pile. If they change the order in which the grains are stacked, the shape of the pile might be completely different. The individual grains remain the same, but their final arrangement depends entirely on how they were added. Similarly, infinite sums do not always follow a single path to one answer. Small changes in sequence can lead to vastly different results. This also connects to the idea of limits, a fundamental concept in calculus. When working with an infinite sum, we do not add everything at once. Instead, we look at the sum as it grows by adding more and more terms. If a series is absolutely convergent, this process always leads to the same result. But if it is conditionally convergent, the final outcome is shaped by the specific order in which terms are introduced. For many people, this discovery feels counterintuitive. It challenges the way we think about numbers and suggests that infinity does not behave as expected. But once understood, it becomes a powerful tool for analyzing infinite sums and understanding how numbers interact at large scales. It is a reminder that in mathematics, even the most basic concepts can take unexpected turns when extended to infinity. This theorem is an example of how mathematics continues to reveal surprises. It shows that even something as familiar as addition can behave in strange ways under certain conditions. It also highlights the importance of carefully considering assumptions when dealing with infinite processes. What seems obvious in one setting may not hold true in another. Understanding these ideas helps build a deeper appreciation for the complexity of numbers and the ways they shape the world around us. Imagine a set of boxes and a set of objects. If there are more objects than boxes, at least one box must contain more than one object. This idea is known as the pigeonhole principle. It is simple and seems obvious in everyday life. If you have 10 socks and only 9 drawers, at least one drawer must hold more than one sock. Dirichlet's box paradox takes this principle and applies it to infinite sets. This leads to results that seem strange at first. It shows that in some cases, even when it looks like there is enough room, objects must still share space. The paradox arises when we try to extend our intuition about finite numbers to the infinite. Consider a variation involving real numbers between 0 and 1. Imagine that you divide this range into an infinite number of boxes. You might expect that every number can have its own separate box. But the paradox shows that, in certain ways, numbers must share boxes. The reason comes from the structure of infinity. To see why, think about decimal expansions. Every real number between 0 and 1 has an infinite decimal representation. Now assume you try to assign each number to a unique box based on its first decimal digit. Numbers that start with 0.1 go into one box, numbers that start with 0.2 go into another, and so on. This seems reasonable because there are 10 possible first digits, 0 through 9, and infinitely many numbers exist. Now look at the second decimal digit. If you try to separate numbers again based on this digit, each original box splits into 10 more boxes. You can repeat this for every decimal place. This process creates infinitely many boxes, yet numbers must still share. The reason is that real numbers are uncountable, meaning there are more of them than there are natural numbers. Even though it feels like there should be enough boxes, the way infinity works forces some numbers to occupy the same space. A different version of the paradox comes from dividing people into categories. Suppose you have an infinite number of people and an infinite number of different hats. Each person gets a hat, and you want to sort people into groups where everyone in a group has the same hat color. Since there are infinitely many colors and infinitely many people, You might expect each person to have a unique color. But in certain mathematical setups, at least one color must be worn by infinitely many people. This is counterintuitive because it seems like infinite variety should prevent repetition. The paradox reveals that our understanding of infinity is often flawed. Another way to see the paradox is to think about birthdays. Imagine a planet with an infinite population. Each person is assigned a birthday, chosen randomly from 365 days. Since there are infinitely many people, you might expect that every possible birthday has an infinite number of people celebrating it. However, intuition may suggest otherwise. You might think that if birthdays were spread out enough, some days could have fewer people. The paradox shows that in an infinite setting, not only does every birthday get used, but each one must be shared by an infinite number of people. This connects to an idea in mathematics known as the infinite pigeonhole principle. The regular pigeonhole principle applies when you have a finite number of boxes and more objects than boxes. The infinite version states that if you place infinitely many objects into a finite number of boxes, at least one box must contain infinitely many objects. That seems natural, but what happens when you also have infinitely many boxes? The paradox arises when infinite objects are placed into infinite boxes, and yet some boxes still end up containing more than one object. A related example comes from number theory. Think about the rational numbers, which are fractions like 1/2, 3/4, or 5/8. These numbers seem spread out because they can get arbitrarily close to any real number. But there are infinitely many rational numbers and infinitely many irrational numbers. Yet between any two rational numbers, there exists an irrational number. The pigeonhole principle suggests that rational numbers must cluster in certain ways, even though they seem evenly distributed. Another strange result appears when you try to distribute points on a plane. If you take an infinite set of points in a square and try to separate them into regions, some regions will always contain more than one point. Even if you make as many divisions as possible, there will always be clusters of points together. This occurs because of the way space and numbers interact in an infinite setting. Dirichlet's box paradox highlights how infinite structures behave differently from finite ones. Our intuition, shaped by everyday experience, tells us that more boxes should mean more space. But when dealing with infinite sets, that logic breaks down. Infinity is not just a large number. It follows its own rules. This paradox is useful in many areas of mathematics, including combinatorics, number theory, and probability. It helps explain why certain problems do not have simple solutions. It also provides insight into the nature of real numbers, rational approximations, and the way infinite sequences behave. One practical application of the paradox appears in computer science. Consider how data gets stored on servers. If you have infinitely many files and infinitely many storage locations, it seems like each file should fit in its own place. But storage systems follow constraints, much like the paradox suggests. Some locations end up being used more than others. Load balancing, hashing, and database indexing all rely on principles similar to this paradox. Another real-world example is DNA sequencing. Scientists try to categorize genetic sequences into groups based on similarities. With enough data, patterns emerge. Even though the number of possible sequences is vast, repetitions and shared structures always appear. The paradox explains why infinite diversity does not mean unique placement. It also applies to linguistics. If you try to categorize all possible sentences in a language, you quickly find that some structures repeat. Even if a language has infinite possible sentences, grammar rules force some structures to be used more than others. That is why common sentence patterns appear again and again. The paradox challenges how we think about classification, grouping, and distribution. It shows that infinite sets behave in ways that seem unnatural. It teaches that even when we think there should be enough space, mathematics can prove otherwise. It is a reminder that intuition is not always reliable when dealing with the infinite. Understanding this paradox helps in many fields beyond mathematics. It changes how we see probability, logic, and even everyday problem solving. It shows that the act of placing things into categories always has limits, even when there seems to be endless room. Infinity does not behave like a large number. It follows its own set of rules. Alhazen's paradox comes from the study of optics, the branch of physics that deals with light. It appears in the problem of reflection and refraction, where light changes direction when it bounces off a surface or moves between different materials. The paradox arises when trying to determine the point at which light reflects off a curved surface like a sphere. The issue is that, in many cases, there are two possible answers instead of one, which challenges the assumption that a single, clear solution should exist. To understand this paradox, imagine a smooth, shiny sphere like a polished ball. A light source sits at one point outside the sphere, and an observer stands at another point. The question is, at what exact point on the sphere does the light reflect in such a way that it reaches the observer? In the case of a flat mirror, the answer is straightforward. The law of reflection states that the angle of incidence, or the angle at which light strikes the mirror, equals the angle of reflection, the angle at which it bounces away. With a curved surface, things become more complicated. A sphere is symmetrical, meaning many different paths exist for light to travel. When solving the problem mathematically, two solutions often emerge. That means light could reflect off the sphere at two different points and still reach the observer. This result seems strange because in many physics problems, especially those involving motion and forces, a single correct answer is expected. But here, both solutions are valid. To see why this happens, consider how light behaves when it meets a curved surface. A beam of light spreads out in different directions when it strikes an object, and each individual ray follows the rule of equal angles. When a sphere replaces a flat mirror, some rays that follow the reflection rule still reach the same target. Instead of one unique reflection point, there can be two. This is what makes the problem different from cases with flat mirrors, where only one solution exists. The paradox also appears in refraction, which is when light bends as it moves between different materials, like air and water. In water, light slows down and its path changes direction. The same question arises: at what point on a curved boundary does light bend in such a way that it reaches a given target? Just like with reflection, the mathematics of refraction often leads to two possible answers. A real-world example of this effect happens in lenses, especially in eyeglasses and camera lenses. When light enters a curved lens, it bends toward a focal point, but because of the way curved surfaces work, multiple paths exist that lead to the same final destination. This is why certain optical systems produce multiple images of the same object under certain conditions. This paradox has a long history. The problem of finding the correct reflection point on a sphere dates back to ancient Greece. The mathematician Ptolemy studied it, but he did not find a general solution. The Arab mathematician and physicist Ibn al-Haytham, known in the West as Alhazen, explored the problem in detail in the 10th century. He attempted to solve it using geometry, and his work influenced later scientists studying optics. Even in modern physics, the problem still appears in various forms, especially in areas like computer graphics and engineering, where accurate reflection calculations are important. Understanding Alhazen's paradox can also help explain natural phenomena. One example is how light interacts with raindrops to form rainbows. A rainbow occurs because sunlight refracts as it enters a raindrop, reflects inside the drop, then refracts again as it exits. The paths of light inside the drop are not always unique. In fact, some light rays follow different paths, but still emerge at the same angle. This is why rainbows sometimes appear as double or even triple arcs. The same principle applies in other optical effects, such as mirages, where light bends due to temperature differences in the air and creates the illusion of water on a hot road. One of the challenges in solving this paradox is that it requires solving an equation that does not have a simple algebraic solution. Mathematicians eventually showed that the problem leads to a type of equation known as a quartic equation, which involves terms raised to the fourth power. Unlike equations involving squares or cubes, which often have straightforward solutions, quartic equations are more complex. In many cases, they do not have simple formulas and must be solved using numerical methods or approximations. The fact that two solutions exist may seem unusual, but it fits with a broader pattern in physics and mathematics. Many problems, especially those involving waves and optics, have multiple valid answers. In wave physics, for example, interference patterns occur when two or more waves overlap and produce multiple points of constructive or destructive interaction. In quantum mechanics, particles often take multiple paths simultaneously, leading to results that seem counterintuitive. The idea that a system can have more than one valid outcome is not unique to optics. This paradox also has practical applications. Engineers designing optical devices, such as telescopes and microscopes, must account for multiple reflection paths to ensure clear images. In computer graphics, realistic rendering of light requires solving reflection problems accurately, especially when simulating curved surfaces. Video games and movies that use 3D rendering techniques rely on these principles to make scenes look realistic. Even in architecture, understanding how light interacts with curved structures can influence design choices to optimize natural lighting. Another example of how this paradox appears in real life is in satellite communication. Signals sent between satellites and Earth often reflect off atmospheric layers, the ocean, or even the moon. Because curved surfaces can lead to multiple reflection points, engineers must account for this when calculating signal paths. Understanding how light and radio waves behave in these situations helps improve communication accuracy and reduce interference. The paradox also connects to astronomy. When astronomers observe distant stars and galaxies, they often use large mirrors in telescopes. Because these mirrors are curved, multiple reflection paths exist, affecting how images are formed. Some telescopes use adaptive optics to correct for distortions caused by these effects. The study of optics, including problems like Alhazen's paradox, plays a key role in improving how scientists gather information about the universe. Despite its apparent complexity, the paradox ultimately reveals a fundamental truth about light. Its behavior follows precise mathematical rules, but those rules do not always produce a single obvious answer. In some cases, multiple solutions exist, even if human intuition expects only one. This is a common theme in science and mathematics. Many problems that seem straightforward at first turn out to have surprising or counterintuitive results. Alhazen's paradox challenges the assumption that every problem must have a unique answer. It shows that light, when interacting with curved surfaces, does not always follow a single predictable path. Instead, it can take multiple routes to the same destination. The paradox is not a flaw in the laws of physics, but rather an interesting feature of how light behaves. By studying problems like this, scientists and engineers gain deeper insights into the nature of light and its applications. Whether in designing better lenses, improving computer graphics, or exploring space, the principles behind this paradox continue to play a role in modern science and technology.